Check. 2.
All right, thank you.
Cool.
Good morning, folks. It's time to start heading down to your chair for the day. Those of you that have posters, they go to room 432, please. Those of you that were in the subaqueous committee yesterday, at break, you will meet in the corner over there to vote for your new chairperson. I have a pink phone by my computer here. Somebody's missing a phone.
Good morning, everyone. Hello. Good morning. Good morning. Good morning, everyone. Okay, grab your coffee. Grab your coffee. Those were great lines yesterday about the height of the podium, weren't they? That's the only joke I'm going to tell. Okay. Okay. So today we're about to get rolling, and we are going to get rolling right now. My name's David Hopkins. I'm from North Dakota State University. Again, welcome. It's great to see you all here. We've got a beautiful place to be. So today, let's just get right going. Our first speaker is Dr. David Franzen, who's our extension, our soil specialist. He's been with NDSU for many a year. He's my co-author, he's my mentor, and he's got a bullwhip that he uses from time to time. Oh, he sure does. So I think that seems to be working. And I'm going to turn this off.
Well, it looks like it's working. All right, so thanks, Dave. I told him there was a time limit on an introduction. You didn't even have to show a card. So anyway, my overall topic is industrialization of agriculture and how that's changed. And so since nobody's going to throw me away for doing my own thing, I'm kind of going to use that to talk about the transformation of agriculture in North Dakota for ill, and then also we're using it now for good. So the soils, as you've learned from other presentations here in the state, are at least 10,000 years old. Very nutrient-rich prairie soil, records of 2-3 feet of really black topsoil when people settled here, and very grazed. It was a grazed system. The only trees around were along the rivers. We had very, very high amounts of nitrogen, phosphorus, potassium, all the nutrients that a plant could possibly want at the time of settlement. So you had a couple of really good presentations yesterday. And so I just want to, I'm a context person, so I have to do this. I have to do it. I have to set the table. So before the Europeans came in and started agriculture, the natives also farmed with their native plants, but they didn't do it like Europeans did. They moved close to the rivers and kind of did it like the Egyptians did, many years ago, where the flood waters would come in and they'd come in and plant crops. So minimal soil disturbance. There's a picture probably of an inland area with a bone hoe back a long time ago. So we've all seen these nice pictures and dances with wolves where there's no bones anywhere, but that's really not how it was. I mean, this is probably excessive, but there were bones everywhere. You can find letters back home for people that are south of Fargo, for example. I found a letter of a farmer and says it's really hard time plowing because I go about 10 feet and I run up against a bone. I have to pull it out. I go another 10, 15 feet. I hit a bone. I got to pull it out. So some of it is just from natural death. Some of it is from the native hunts, and some of it was from the great slaughter. But there were bones everywhere, just millions of tons of bones. So this is a picture from a sighting in Minot. There was a brisk trade for about 20-ish years from the mid-1880s until into the 1900s. This followed a similar kind of brisk trade down in the southern plains where they gathered buffalo bones and sent them east. And so they were used for a lot of different things. Anybody ever remember the Revenant? Remember the Revenant? Remember that picture? Okay. So this comes from Detroit. This is the end product, for the company that bought some of the bones, and they were scattered everywhere. The end markets were everywhere. So that's that. So the context is done, and I can breathe easy. So when people came in to farm the land, of course, They found the soil was remarkable, that had they ever seen a soil like that? If they came from the east, if they came from Bergen, Norway, they came from Germany, they'd never seen soil like this at all. Thus our motto, strength from the soil, from North Dakota. So here's a very proud farmer, somewhere around 1910, 1915 roughly, in the Red River Valley. See all the trees? See how fluffy that soil is? Why do they do that? It's because, have you ever seen those old planters in a museum or something like that? You could probably pick up a gang with, if you were built, you could probably pick up a gang because they're very light, not a lot of down pressure, and so it had to be fluffy to get the seed in the ground. After all, that's what you did in Norway, Germany, Ohio, Virginia, wherever you came from, right? Where the strong wind was what, 10 miles an hour? And then you came here, and you have to stand like this, to avoid falling over. On most days, this has been kind of a quiet year, but in most years, a normal wind is 20, 25 miles an hour every day. So this was all right. People lost soil in their records of, just in passing, people are talking about the ditches filling up with a windstorm, but nobody really cared about it because the soil was just so deep. But then it started to dry out in the late 1920s. It's a picture from Minot, growing corn in Minot in 1920 something. Can you imagine that? Anyway, somebody tried to do it and didn't work out well. And so by the early 1930s, the USDA had come out with a map of the wind erosion susceptibility, and of course we're in it. We're in it with Texas and Oklahoma and Nebraska and Kansas and South Dakota. We're just as bad and just as dirty, and really it goes up into Canada as well. So there was a lot of soil lost, a lot of soil moved. This is just east of here, about maybe 30, 40 miles, something like that, and south maybe 30 miles. This is a fence built on top of a fence after a series of dust storms. These are huge, huge things. So this is, I don't know, maybe it's because the people up here were just Scandinavian and really didn't want to talk very much or anything, but it took a while for word to really get to Washington that this is really an issue. So Russell is his last name, was a FSA employee and came out to western North Dakota and filmed took pictures of some of the dust out here. This is my own personal copy. This is about during the day in Huron, South Dakota, which is just south of the North Dakota border. This is I don't have my glasses on, and it's like 11 o'clock or something like that in the morning. Yeah, 11:55, so it's about noon, and those are street lights on. You can kind of barely see the car, in the middle of the day. Can you imagine living through this, days at a time? There's a dust storm rolling in. It looks like you're in Abu Dhabi or something, but here we are just south of the North Dakota border near Watertown, and a big dust storm coming in. You see these pictures from Kansas and Oklahoma, but they're kind of rare from up here in Dakotas. This is south of Pierce, South Dakota, and one of the big black blizzards of the 1930s. So that was then, and it's all fixed, right? Well, it's not. So, but it's remarkable how many farmers, especially if you get in the Red River Valley, not so much out here, there's a lot of no-till here, and I'll talk about that in a little bit. But in the Red River Valley, there's a lot of farmers that really think this is kind of a trivial thing, where they have a dust storm, it fills up the ditch, they get the backhoe out, they put it back in the field, everything's good, right? So, but we have satellites now, and so this is a picture from the Palouse, and how much of that dust that's blowing around gets in the ditch. That plume is over 100 miles long. There was in the news, I think it was last week or something like that one of the services picked up that the southern United States was getting dust plumes from the Sahara over it. And so these things move around the world. So how much of that goes in the ditch? A really small amount. And all the good stuff is in the air. The junk is in the ditch. So this is an illustration. Even back in the 30s, people recognized that this was a three-dimensional event. This is a Bismarck Tribune article from remarking on a dust storm back in the 1934. And it noticed, I underlined it there, the line that says, several aviators that are coming into town, paraphrase, reported that dust was encountered at levels up to 14,000 feet. And this dust storm lasted several days, and as you can see from the article, this is not the only dust storm that happened in this year. So these things are three-dimensional, and they blow a long, long way. So we lost a lot of topsoil, and I estimate conservatively 12 inches from hilltops, 8 inches from slopes, average of 6 inches, and so that's 30 billion tons of soil that was lost in the state during the 1930s. And what I try to do in my presentations is to link soil fertility along with soil conservation. And this really is an important tag, and it's not just a marketing gimmick, but it really is that there was a lot of fertility in this material, that people went out, I think it was, the paper said it was in Central Park, somewhere in New York City, took a cupful, analyzed it, and it would many, many more times the phosphate, the nitrogen, the potash from there as where they thought it originated in Kansas or wherever it was anyway. So it was just lost a lot of fertility during that period of time. So the question is, other than just thinking that it goes into the ditch, why aren't growers and landowners more worried about this? And the answer, I'm sure, is that they mask the effects of this with tillage. There's no check strip out in the field, right? It's just the whole field. So no check strip. So on the left here, you have maybe an original soil where you have that nice big thick A, you got a very well-established B, and then you got the parent material or whatever it is underneath. And so you plow and it blows and it plows and it blows and you're okay for a while. It's all black, 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 black. But then you start getting into the B horizon and it's really not as black, but the person looks out the back window of the tractor and it still looks black to them. And then they plow and plow and plow some more and you mix more B and more B and more B, and so pretty soon you get the column on the right, which is what a lot of our soils are here in the state right now, is that you got this poor reflection of a mix of the old A and the old B, and you're going into the C and they look out of the back of the tractor and it still looks black to them. But it's not nearly as black as what it was before. So Dave Hopkins here, my esteemed colleague, went out to a number of places where there were barn soils, and the NRCS had sampled these and characterized them back in the 50s, 60s. And so he went back to the same places. They didn't have GPS back then, of course, but he made transects and characterized them and found that during that period of time, was it 50 some years or something like that, they lost, what, 19 inches of topsoil during that period of time? Just gone, and the farmer had no idea. And you see the picture there on the right, where you have that dark layer, and then you have stuff underneath. That's what most of the soils in the state look like now. That's really what they look like. That's not an exaggeration, that's just common. All right, so there's some additional evidence of topsoil loss, and that comes from our old soil surveys from Divide County, which is in the very northwest part of the state. In 1900 soil survey, they described the Divide soil surveys, which are some even in the southwest, but mostly up there. Maybe 16 inches of very black topsoil, I would assume over 6%. And today it really doesn't have any black topsoil. I worked up in that area and you get about 3%. Maybe if you're lucky, it's about 6 inches deep, light gray topsoil, estimated loss of at least a foot. I know it's at least a foot. And then in Cass County, where Fargo is, it's about 50 miles east and west or so. It's a very big county. A wheatland soil, as you go west of Fargo about, what would it be, 25 miles, you get to the wheatland exit, you go take a right, and the wheatland's right there. I've had studies in that area before too. So the soil survey said it has 2 foot of topsoil with organic matter of 6.9%. And in the areas I worked, it has 2% organic matter, and so they've lost all of it. They lost it all. And in Miami loam, they bucketed a lot of soils. You know, we parsed out different things, but you can assume that something like a Bearden, at least a Bearden, is within that Miami soil. 3 feet of the 7% organic matter. And today, if you go out to a Bearden, almost anywhere, it's around 6 inches of 4%. So they probably lost 2.5 feet. And a Fargo soil, and you can imagine where that's from, 1903, 2 foot of very black topsoil, and today 6 inches is pretty common. So there's further evidence. All right, so here's more evidence, and Tom DeSutter said, all you have to do is just tell them that you're kind of the mentor with the land judging here in the state, and you'll be one of them. Okay, so here's 2 years ago, west-northwest of Grand Forks, we just happened, had practice pits and contest pits, and this is one of the pits that was dug, and just so happened to expose a buried A horizon from before the Dust Bowl or during the Dust Bowl. But there's that really light 2% topsoil over that really dark layer. And that really dark layer, I took a sample out of it, and even today it's 5.9% organic matter. You can't find a 5.9% organic matter soil within 30 miles of that place. So, back to fertility in topsoil, you can about 2,000 pounds of phosphate an acre in a 6-inch slice of soil. That's just usually what you find. So if we've lost another 6 inches of topsoil since 1940, which is probably conservative, we've lost another 12.5 million tons of phosphate, 40 million tons of nitrogen, equivalent to about 75 years of nitrogen and phosphate application at today's present rates. The cost of this stuff, if we've lost 2 foot of topsoil from, say, that wheatland site, if you figure out, if you do the math for how much nitrogen and what nitrogen was worth a few years ago, it's not quite that much now, but just the nitrogen in that topsoil is worth $12,000 an acre. So it's all gone. It would have been used at some time. But, all right, so that's the ill side of technology. Dave Hopkins kind of suggested that I show pictures of Big Bud and deep rippers and all this stuff, but you've seen tractors before, right? So you kind of get it. All right, so we got that. So we have all those big things. And but we also have used technology in the last 50 years or so in order to start to improve the soil, and that means getting so that we could do a no-till, modified no-till systems. Was no-till possible in 1885? Was it possible in 1930? Was it even possible in 1950? No, of course not. There weren't the tools, there wasn't the machinery, and there certainly wasn't the everything else that goes into ag technology that makes these things work. So these are the build-up things. So this is not that far away from here. Center, North Dakota, visited a farm a number of years ago with a consultant, and he'd build a strip-till unit. Very simple, coulter, that's the kind of a modified anhydrous knife, and then covers behind it. But it works, So you clear out this area, you leave most of the stubble around, you minimal disturbance, you crack the soil, which in these kalinitic to illitic type clays that we have in this southwest to central part of the state, that's important once in a while to crack those if you can, especially after wet years where you can't be as patient as you'd like to be. So people have gone to more of a strip-till type system, and I think you're familiar with strip-till. You crack it, you make this little mound, you put fertilizer maybe down on the bottom of it if you like, but you don't have to, and then by the spring that mellows out, it's still cleared, you have trash whippers or residue managers, whatever you want to call them, in front of the planter wheel, and you just put it right down that slot. And the GPS we have today allows that to happen without the person going crazy because they're looking at the row all the time. So they don't have to do that. They can watch TV or something, and this can all happen. So this is a farm I work with in the southeast part of the state. The person's been no-till for 50 years. The last 15, 20 years or so, he's been strip-tilling his corn. That field that year, well actually it wasn't that year, but in 2015 or 16 or something like that, the field made well over 200 bushel of corn at all. You know, the standard thing for people that are in conventional till country in the Red River Valley is no till equals no farm. We'll tell that to the champion corn grower in Virginia with 500 and some bushels an acre that's been no till for God knows how many years. And this farmer in particular, these plots we were in were going 240, 250 bushels. There's no problem with this kind of system. And beets are people also getting into strip till with sugar beets. They're probably the touchiest kind of crop that you can put into a no-till system, but if you use the strip till, it works really well. You can tell when something is no-till, when you leave the stubble and when you can't, and those of you that work around here or have worked around here have seen this all the time, that you go around in the fall of the year, things have dried out a little bit, and it doesn't take that long because the humidity is usually pretty low. And the no-till is just fine, and then the clueless neighbors in the background are the dirt's blowing everywhere. So here's some known positive soil fertility benefits of long-term no-till. We have about 50 pounds of nitrogen per acre less required. It doesn't come from mineralization. It comes from being able to, the microbes are sequestering more nitrogen, and there is greater asymbiotic natural organism, bacteria probably, that's going on. So the soil test phosphorus also tends to be greater on the long-term no-till. If you want to find a really low P-testing soil, you go into parts of, you go into the neighborhood where there's still conventional till people where their soil blows away every year, and that's where you'll find the lower soil test P. This is the aftermath of a storm, but just east of the river, Hawley, Minnesota, where the soil from the neighbors have deposited on the field to depth. You know, that's, you know, thanks for the fertilizer. So the first people on the block that are no-till get the neighbor's fertilizer. So here's some observations, long-term no-till versus conventional. This is replicated stuff. This is just things that I've seen. Going to an area out in Beach, the very western part of North Dakota, right before you hit Montana, well over 40 years of no-till when I was working out there. The organic matter on this farm was 3.5%, and right across the fence it was 1.5%, in the same, you know, quote-unquote soil. In southeast North Dakota, and near that farm that I just showed you here a few minutes ago with the strip till, it was over 40 years of no-till. As organic matter is 7%, and the conventional neighbor is 3.2%. And in addition to that, in Rutland, which is more well-watered compared to Beach by a long shot, the high organic matter layer had reached 10 inches in depth. And so this is one of the shortcomings. It's one of the shortcomings of no-till programs across the country, is that we're just assuming that we're just building it up at the very surface. And so people that have been in no-till for a while, you're not eligible for the program. But they really should be, because maybe they've reached a plateau at the surface, but they're developing the depth. So they're still sequestering carbon. So I don't know. If you know anybody in Washington, you might want to let them know. So the end shot is that technology can help or hurt the soil condition, and it's really kind of up to the farmer what they decide to do. Because we're not 1930 anymore, we have a choice. We can do one or the other. So with that, I just open it up for questions and we'll go from there.
Do we have any questions for Dr. Franson, folks? Comments? Over here.
Hi there. I think it's really interesting, some of the numbers that you had up there in terms of the amount of soil loss that's occurred over time. So recently I participated in one of the FAO's mapping projects where they tried to map black soils around the US. And so looking at the data that we did have, it was really interesting. Whenever I tried to generate those maps, they have this thing called black soils, which is semi-analogous to mollisols, but it has a deeper thickness requirement. And so anytime I generated those maps, you know, there wasn't nearly as much as one would think based on our historic understanding of, you know, what soils looked like along the Great Plains and things like that. And so I think it would probably make a good addition to your presentation here, in part because every time I would show those maps to people, they were like, where are all the black soils? It's like, well, there are not that many that are left that are that thick. So 25 centimeters is actually quite a lot. I mean, our molic definition, what is the threshold now? It's only like 18 centimeters. So depending on how you play with the numbers and generate the maps, you can get different looking maps. But in general, there's not as much as I think people think that there should be.
Yep.
So that's not a question, a comment, but.
Yep, thanks for the comment. Okay, I'll be around here till about noon.
Great. So if you have questions for Dr. Franzen, please address them. Our next speaker is virtual. This is Dr. Sanderman, who will be coming to us soon, I believe. This is Jonathan Sanderman from the Woodwell Climatic Research Center in Pennsylvania, I believe, measuring soil carbon, unique considerations for climate mitigation. So hopefully we can get Jonathan live here with us in just a moment. Okay.
All right, so we're ready for you to start.
Okay, thanks so much, Wade, and thanks to all the organizers. It's really a great honor to get the chance to talk to this group, and I apologize I can't be in Bismarck in person. So what I'm going to talk about today is, really just some ideas around how we measure soil organic carbon when thinking about climate mitigation. And I have to say a lot of these ideas have really evolved significantly over the past couple of years, thanks to a really fruitful collaboration I've had with Environmental Defense Fund that we call Consensus on Carbon Markets. So the terms MRV and MMRV get thrown around a lot these days, which MMRV means measure, monitor, report, and verify. So as scientists, we're generally focused on the measure and monitor parts. The reporting is primarily the legal requirements of some sort of carbon market program, and verification is critical and can take on different forms. We could just verify that practices are in place. We could verify that sampling was done correctly. We can verify the outcomes. In other words, we could check model estimates, check to see, basically independent check to see if more carbon is in fact in the ground. But the verification often isn't considered in discussions around monitoring, but really this should be a closed loop system, and their verification kind of brings us back to ensure that the monitoring program is robust. And so an MRV or MMRV system is really fit for purpose. Are we designing something to track progress towards incentive programs or national targets? Are we a corporation trying to track progress towards a net zero target? Or is this a voluntary carbon market where we're selling carbon offsets and we really need to ensure that real atmospheric CO2 reduction is going on? So these are the main talking points that I want to hit on today. First, we really know how to measure and map soil organic carbon. How to do it cost effectively is a bit of a challenge right now. Third, detecting soil carbon change is much more difficult than measuring soil organic carbon stocks. And finally, climate smart agriculture is really about the difference from the business as usual scenario, or what would have happened if you didn't improve those management practices. So first, measuring soil organic carbon really isn't that hard. We collect a number of cores or dig soil pits, divide the core into segments of the pit into horizons, send those samples to the lab to measure soil organic carbon, bulk density, coarse fragments. If we do this at enough points, we could come up with an unbiased estimate of the mean for a field, or use these data to map the distribution of soil organic carbon. So this process isn't difficult, it's just time consuming, and therefore it's difficult to do cost effectively. And so this is where a lot of innovation is currently happening, both in academic government research as well as in kind of the ag tech sector. There's a whole bunch of startups focused in this space of low cost soil carbon monitoring. So there's all sorts of sensors coming online, ranging from more traditional lab-based infrared spectroscopy methods to field deployable spectroscopy methods to various combinations of existing and new proximal sensing technologies. So what about soil carbon change? First, it's worth looking at how much change we're expecting to see. So sometimes we hear pretty large numbers, 2-3 tons of carbon per hectare per year being thrown around. I think in reality, the expected gains from modest improvements to agricultural land, such as shifting to reduced or no-till, incorporating cover crops, are pretty modest. So I'm going to show a couple of histograms of results from various meta-analyses. First is one that I led back when I was working in Australia, looking at best management practices in Australian cropland. So we found the mean response of about 1/3 of a ton of carbon per hectare per year, with quite a distribution around that mean value. Next, this is probably the most cited meta-analysis on cover cropping. They also found the mean response of about 1/3 of a ton of carbon per hectare per year, with an even wider distribution. And finally, a synthesis of improved grassland management practices found also a mean response of about 1/3 of a ton of carbon per hectare per year, with a, again, even wider distribution around that mean value. So all these histograms show that gains can be large, but on average, they're modest. And actually, in many cases, the climate smart intervention resulted in no change in soil organic carbon. And so this is important to keep in mind that we are trying to detect very small changes quite often. And so this idea of being able to detect 1/3 of a ton of carbon per hectare per year change against a large and variable background soil carbon stock is like trying to find a needle in a haystack. We could do some simple back of the envelope math here and look at what does 1/3 of a ton of carbon per hectare per year actually translate to. So this is a property on the right that I've been working at in Colorado that has a mean topsoil organic carbon value of 2.3%. So as all the darker shades are irrigated alluvial land, so it's really productive pasture. And if we just assume bulk density is 1 and doesn't change, 1/3 of a ton of carbon is equivalent to an annual increase in soil carbon concentration of only 0.01% annually. That is basically completely impossible to measure with today's technology. So we could conduct a classic power analysis based on this prior information, so looking at the variation in that field. And this is typical results that my colleague Emily Oldfield put together. And that last example would fall along the blue line with a standard deviation of 0.5 and a mean of about 2%. And so after 5 years, if we wanted to detect that level of change, we're talking we need 30 samples per hectare, or 12 cores per acre to detect that level of change with a power of 80%. So now this is a real world example that some of my colleagues at Yale have provided. So they embarked on a high-density soil sampling campaign across a number of Midwestern ag fields. They collected 10 cores per hectare from these fields with differing levels of in-field soil carbon variation. So the most variable fields on the top with a coefficient variation about 14%, and the least variable is on the bottom with a coefficient of variation of about 10%. They conducted an experiment where they subsampled from the entire population of soil cores within each of these fields. So essentially, assuming that the highest density sampling is the working truth and that that's an accurate representation of carbon distribution with these fields. And then they randomly subsampled 100 times at lower sampling density, 4 hectares per sample on the left and 1.2 hectares per sample on the right. So that's pretty high. That's a higher sampling density than almost anyone is embarking on. And these histograms show the results of the distribution and soil carbon outcomes that you would get at these 2 different sampling densities. I've added these orange bars just to highlight plus or minus 1.5 tons of carbon per hectare. So that's kind of the range that we're expecting to see after 5 years. And we could see that just by chance, you will likely get a value much higher or much lower than the true mean of these fields just because of this in-field variation. So this problem of not accurately representing the mean leads to the statistical phenomena called regression to the mean. So if we run another thought experiment with these samples, we could essentially just resample the same field with absolutely no change after 5 years. And just by chance, it's really likely that we're going to detect a significant change, whether positive or negative, because it's highly probable in that first round of sampling that we're going to get an estimate that's slightly lower than the mean or slightly higher than the mean. And so we essentially have no confidence that we can detect change at the level of a field unless we embark on an extremely high density soil sampling campaign. So essentially that's my first takeaway message. Field level detection of soil carbon change is really a fool's errand. I added this asterisk because I think some of the technology I mentioned earlier can actually get us out of this problem if we can actually sample these fields at high enough density rapidly and at low cost. On this slide, I also just want to briefly mention the Conservation Evaluation Monitoring Activity 221, which recently came out. The recommended sampling density in this SEMA 221 program is about 1.5 hectares per sample. So that's slightly lower than the higher density sample I gave earlier. And based on those results I just showed, to me, this means this program is actually going to be providing highly unreliable data back to producers on soil carbon change. It's highly likely that even if they had no change on their field, we're going to be telling producers that their soil carbon levels are changing higher or lower simply because we have an underpowered test of soil carbon change going on in this program. So essentially, spatial scaling is the way out of this predicament. Because variance in soil carbon is bounded as scale increases and the random errors we get within the field tend to cancel out, it should be much easier to detect change. However, there is a critical question that needs to be addressed for a regional monitoring program. What are we thinking about as the individual or the unit of study? Many groups, especially in voluntary carbon market space, are treating points within large strata as the individual unit of measure. I think that's actually incorrect. And as this image shows, the human footprint is really based on polygons or vectors, essentially field boundaries. And so the fundamental unit of study actually should be the field. And then I think if we consider the field the individual, we actually need to represent the mean for each of these fields, not just a randomly allocated point within that field and assuming that the management of that entire 20, 30 hectare field is represented by that one point that you happen to randomly place in that field. So going back to this great data set that my colleagues at Yale have put together. They ran another thought experiment where they have 100 fields enrolled in an aggregated project. In this case, each field had a similar coefficient of variation, but they applied an arbitrary and randomized change averaging 3 tons of carbon per hectare imposed on each field's soil carbon distribution. They then sampled 10, 20, and 30 fields shown as the top, middle, and bottom at 2 different sampling densities. Again, that lower and higher sampling density on the left and the right. They repeated this sampling of 10, 20, and 30 fields 100 times to see how often they can recreate the true change of 3 tons of carbon per hectare. And now you can see here that actually the random errors tend to cancel out, and you can see the range of values on the x-axis are actually really small here, especially at the higher sampling density in the right-hand column. So this means that we can measure actual change with confidence. In fact, the gray shaded region shows plus or minus 1 ton around that mean value of 3. So in fact, in that upper right example, just sampling 10% of the fields at this higher sampling density, over 80% of the time, we're getting an accurate response. We're getting an accurate measure of the true response that these fields underwent. So, second takeaway, at moderate sampling density, it's possible to measure soil carbon change in a pooled project. Now, the final point I want to make is that natural climate solutions or climate smart agriculture isn't really about measuring natural carbon stocks and flows. Quantifying outcomes in a climate smart ag program is really fundamentally different than an inventory where we're just looking at changes on the landscape year over year. It's really about carbon removal or the avoided emissions due to the human intervention. And so the core concept here is the activity needs to be additional. In other words, different than the business as usual. So we need to know what's happening in this counterfactual situation. This is difficult to do and almost never done well across natural climate solution projects. So work I published in Australia synthesizing field trials that actually had time series data shows that adopting best management practices was actually just mitigating ongoing losses of soil carbon. So if we only tracked the projects where we implemented the climate smart ag interventions through time, we would get the blue lines here in the middle. So essentially we would show that there's no change going on. But if we also measured the counterfactual scenario, so fields where the practices weren't implemented, we would see that there is a real benefit here. So that means that without accounting for this dynamic baseline, we would be greatly undervaluating the carbon benefits of these management practices. So now this is just a simple cartoon showing these two situations. If we're only measuring a field through time, such as in an inventory, we would have to assume a static baseline. But the reality is this business as usual case varies for a whole number of reasons, including the historic management, current market trends, the climate over the crediting period. And as a result, most voluntary carbon market protocols rightly require, or at least strongly recommend, using this dynamic baseline approach. So from the atmosphere standpoint, actually both of these cartoon examples result in the same net benefit, but the measurements need to be really different or we wouldn't capture any of the benefit from the example on the right. So this baseline right now is a huge data gap, and it's received very little attention, really, despite its critical importance in estimating the true benefits of climate smart agricultural programs. So I really want to kind of wind down this presentation kind of with my stump pitch for federal investment. I think we are already collecting an enormous amount of data, but it isn't always the right data for soil-based climate solutions, or it isn't in the right locations, or just not nearly in enough locations. So essentially what we need for soils is a forest inventory and analysis program where we have repeat measurements collected in a statistically robust way at a large number of points that include all the necessary contextual information to understand why the soil carbon is changing. So just to summarize, MRV needs to be tailored to the goals of the program. We need to try to be able to detect small changes against a large and variable background. I think this is basically impossible to do at the field scale, although emerging technologies may save us here. Therefore, we need to monitor at an aggregated scale. I don't know what the right aggregated scale is, but it's much larger than the unit of an individual field. And finally, these dynamic baselines are absolutely critical, but difficult to measure. And I really think the NCSS is extremely well positioned to coordinate these efforts here. And finally, I think as the NRCS and NCSS thinks about designing a monitoring system for soil carbon sequestration, this old adage, I think, applies. Let's just think twice about setting up a monitoring system before starting to collect soils. So with that, I'll end my presentation, and hopefully I have some time and can take some questions.
Do we have questions? Dr. Sanderman, can you hear us?
Hey, Wade, I don't know if you're talking or anyone's talking. I can't hear anything.
Check 1, 2. Can you hear us?
Can you hear us, Jonathan?
Now I can.
No, you can. All right. So ask away, Greg.
I don't know.
You can't. Turn the microphone on.
Now, there we go. During the methods for sampling was, it appears to me like the sample methodology was to sample per field or a certain density in certain fields. Was the soil type considered, like sampling so many of a certain silt loam, for example? Was a soil series or soil type map units considered in the sampling methodology?
So are you referring to the data examples that I gave, whether the soil type was considered in the sampling design?
Correct. Yes.
So in those data, soil type was not considered. Those fields varied in size from 10 to 30 hectares. And it was essentially a grid that they laid down across the fields and did not stratify by soil type. But I mean, I think what you're getting at is, can we try to reduce some of this variation by sampling within the soil types? And I think if that's what you're getting, I mean, I think you're absolutely right. That's one way to help manage some of the variability we get within a field, is to stratify our sampling. If there are major soil boundaries or if there are topographic breaks, we could stratify by like slope position, summit, slope, bottom. So yeah, so there are different strategies to help overcome some of this field variability that we do see.
Okay.
Great. I think that's all.
Any questions?
Good time for one more.
Yes. Many of the presentations I've seen on soil organic carbon change over time.
Turn on the microphone, please. Turn on the microphone, please.
Can you hear me now? Okay. In many of the presentations I see on soil organic carbon change over time, like the graphs that you showed, there's very little mention of the soil depth that's sampled, whether it's 0 to 15 centimeters, 0 to 30, 0 to 60. Is there any consensus on sampling depth for these carbon markets that are developing?
Yeah, that's a great question. And I mean, you're absolutely right. A lot of those meta-analyses kind of throw everything together. I mean, oftentimes they'll use, depth will be a variable in some sort of mixed effects regression to try to pull out the effects. But there's actually a paper just published out of Europe where they resampled a bunch of long-term trials down to a meter. They might have even gone beyond the meter just to see how deep change is occurring. And their conclusions were, I believe 80% of the change was within the top 30 centimeters. Another 17% was between 30 and 50, but they couldn't detect anything below 50. So their recommendation was to go to 50 centimeters, where, I mean, most carbon market programs say, they generally say the minimum's 30 centimeters, but they allow you to go deeper. And so, I mean, if you're implementing, like if you're putting in some like perennial bioenergy crops or something, you probably want to go deeper than 30. But I mean, that paper that just came out was pretty, I mean, it did, I mean, the authors kind of were criticizing people going only to 30 centimeters, but yeah, at least it's way easier to go to 30 centimeters than it is to go to 50 or 100 in terms of sampling effort. So at least you're capturing 80% of the benefit. So you might be undervaluing the true change a little bit, but not significantly.
Thank you.
Thank you. Thank you, Dr. Simmons.
Okay, thanks everyone.
Thank you. Excuse me, folks. So our next speaker is Danelle Peck, who's coming to us from, forgive me, from Fort Collins, Colorado, and the ARS down there. So.
Not yet, but there it goes. Wonderful. Good morning, everyone. While we're waiting for the slides to come up, it's a pleasure to be up here today and to go on the field trip earlier this week. That was fantastic. I come up here quite a bit. As you'll see in a minute, our Climate Hub serves a multi-state region that includes North Dakota. So I consider this part of my extended home and extended family. It's great to be up here to spend time with you all. Okay, so I'm going to introduce you today to the USDA Climate Hub Network if you're not familiar with us yet, and then just share a couple of tools that we've been involved with that I thought might interest you all. So first, the Climate Hubs. If you haven't heard of us, we're a network of 10 regional hubs across the country. Take a moment, find where you live or work, figure out which Climate Hub region you belong to, or which hub belongs to you. So take a moment for me, and by a show of hands, how many Northern Plains Climate Hub folks do we have in the room? Welcome, there's my family. All right, looking to the east. I grew up on a dairy farm in upstate New York, so my heart belongs to the Northeast Climate Hub. But looking at the hub regions to the east of me, the Midwest, the Southeast, the Northeast, the Caribbean Climate Hub, how many of you belong to those eastern? Nice, well represented. They might have us outnumbered, Northern Plains folks. And then looking to our south and west of me, so the Southern Plains, Southwest, California, and Northwest hubs. Where are you? That's really great. We've got pretty great equal representation across the country. What I'll say, and you'll see in a minute, that our climate hubs are pretty small teams. So it makes it really easy to get to know who is your climate hub director, who's your coordinator, and reach out to these folks and get to know them and think about partnerships. That's the theme of today's presentation. The mission of the Climate Hubs, I think, aligns really nicely with what you all work on, right? We are all out here trying to help our working lands, our farms, our ranches, our forests, have robust and healthy agricultural production or forest and fiber production in the context of a climate that's becoming increasingly variable and changing. So that's our mission as Climate Hubs. How do we do that? What do we really do on a day-to-day basis? The Climate Hubs work in 3 what we call work streams. And so you listed here, the first one, we spend a lot of our time, and I feel like our heart is in the world of outreach, convening, bringing partners together. And a quick example of this first one, a shout out to Louis Tupas and Mike Robotham. They recently funded an outreach activity that our Northern Plains Hub did in Montana. And so also a shout out to to partners at NRCS in Montana. Alex Dado is here today. We did a 2-day training, agroclimate workshop in Billings, Montana. About half of our audience was NRCS, and then all of their partners, Extension, tribes, conservation districts, FSA. So we gathered for 2 days and talked about climate and climate change and agriculture and what they were seeing and experiencing out on the landscapes, why it was happening, and what could we do about it that seems to work well for Montana. So a really powerful convening of partners to advance the conversation about the challenges that we're facing out there with extreme weather and a changing climate. So that's just one example. We also spend some time doing science translation. We don't do a lot of science directly ourselves. Rather, we connect with great scientists like you all in the room today and learn about what you're doing, what are the insights that you're gaining, and which of those insights can we carry with us when we're out interacting with partners in the field to help them be aware of the latest and greatest science, and also to bring messages back from the field to say, hey, here's a new challenge we're seeing. Do you have any science that helps address that, or can we co-develop some science or resources to help address a problem? The last one, we spend a little bit of our time doing tool and technology co-development, and I'll say right up front that we only develop tools when stakeholders ask us for them. We know that there are many, many, many tools out there already, and so we're always listening for, is there a tool that they need? And then let's find the right partners to help co-develop those tools with them. An example of this is GrassCast. For those of you who are in the Great Plains region, GrassCast is the Grassland Productivity Forecast. I have one flyer on my table if you happen to be interested in GrassCast. This is a baby of our Northern Plains Climate Hub, and it helps translate, instead of just handing ranchers a precipitation outlook for the upcoming growing season, we've translated it. We've turned it into a rangeland forecast, get it one step closer to the decisions that they actually have to make. So those are the 3 areas that we work in, and today I'll just give you a few more examples of what we're doing in those areas. I accidentally skipped over that middle one, an example of the science and data synthesis, the National Climate Assessment. Right? We've had the 4th National Climate Assessment since 2018. A lot of the Climate Hub staff were involved in helping write that, and we're about, hopefully this fall, we'll be releasing the 5th National Climate Assessment, led by the USGCRP, of course, but a lot of the Climate Hub staff are involved in helping write that and review that. On a day-to-day basis, I want to help you guys see where you might fit into the Climate Hub, into our day-to-day work. Where do you fit? So this is just an example from my region. You can see the 6 states that I and my team serve. So we're down at the bottom there, a small team, and we're based out of Fort Collins, Colorado, but we're serving a 6-state region. And so we need help out in the field. We need partners and networks. That's our job, is to build networks and partnership, because we can't do it alone. So we partner with NRCS and our conservation districts, our extension partners out in the field, our Farm Service Agency folks. They're the ones with boots on the ground that are out there talking with farmers, ranchers, and foresters. And when they encounter a weather or climate-related challenge, I don't expect them to know what to do with that. Most of us aren't trained in weather and climate. But we hope that they'll think of us and bring those questions that they're hearing or those challenges that they're hearing about to our team. What do we do from there? I will reveal, I'm an ag economist. Dave Archer is also an ag economist, so he can duck under his table over there. I'm an ag economist. I don't have the answer either. But again, as a Climate Hub team, our job is to be a hub. And what do hubs do? We connect. So our job is to be out building relationships with this huge network of partners like yourselves, our agricultural scientists, our weather and climate scientists, so that when we get questions from the field, I don't have the answer, but I know who does. And I can go to them and say, hey, we've got this inquiry from the field. Do you have any resources? Do you have any insights? And if so, then I can carry those back to our partners in the field and say, voila, the magic happened. If it doesn't happen, if we don't have the answers, then really my favorite part as a hub director is to connect the folks in the field with our scientists and policymakers directly and help them, again, convene them and help build relationships so that together they can co-develop some kind of solution. Networks and partnerships, I think, are key to everything that we do, and it's great to see such a diversity of organizations and partners here today. A quick pitch, again, the climate hubs, the regional climate hub teams are small. We each have a director, we each have a coordinator. The rest of our staff depends on funding situations. So right now we're lucky enough to have a NIFA-funded Lee Schmelzer up in Montana, a NIFA-funded ag outreach person to help us better serve the state of Montana. We are bringing on a science communications person at the master's level here in just another couple of weeks. So really excited to get some more science communication staff. Here's the real reason I wanted to put this slide up. We are recruiting and we need help. So our Climate Hub has been recruiting for a postdoc to be located here in Mandan, Bismarck, with our wonderful ARS team. Again, with the goal of making their incredibly relevant science more accessible and be sharing it outward with the folks out in the field that could benefit from it. And again, bringing messages back to the research team. So if you know anyone currently who has a PhD and loves science, but loves to dabble in science, loves learning about different disciplines and talking about it with people, please come and introduce yourself or send me them, send them my way. We're recruiting for that postdoc position. We're gonna be recruiting for a hub science coordinator here in the next year. And then we also are working on an agreement with NRCS to do some climate mitigation outreach, which is gonna be a challenging conversation in my part of the world. And so if you've got those communication skills, keep your eye out for hub opportunities and don't be shy about coming and introducing yourself. One last piece that's really important for our climate hubs is that we have leadership from 3 of our core agencies that support us: Ag Research Service, NRCS, and the Forest Service. So each region has co-leads from those agencies that help guide our regional hubs. So a shout out to Mike Strobel, who's in the room as our NRCS co-lead. All right, I'm gonna skip over this one. And get to the tools that I think you guys might be interested in. So I want to give you some examples of one more example of the outreach and the inreach that we do as climate hubs. This one, knowing how many NRCS folks in the room, we've been doing what we call climate conversations with NRCS, and I don't know if anyone has been lucky enough to sit in on a climate conversation. This is a program that Sarah Thompson has been leading. Sarah is with NRCS in South Dakota, and so she's been helping us go state by state, one at a time, to tailor a 90-minute virtual conversation. Because of COVID, we had to go virtual, but a quick 90-minute conversation, state by state, with NRCS employees and co-designed with their leadership to talk about just some basic climate 101, help us all get on the same page about some basic climate vocabulary. What is the difference between weather and climate? What's the difference between climate variability, and climate change? Like, what's the basic vocab here? What are some trends that we're seeing at a national level, and then dial into the state. What trends are we seeing in your state? And those trends vary really widely by state, so it's important that we tailor these messages. And then we turn the conversation to what is NRCS seeing out in the field? What challenges, what resource challenges are they facing that might have some connection to extreme weather and climate change? And what tools do we have that are working well out in the state, and what challenges remain? So if your state hasn't been among the lucky, I think this is actually now up to 24, and we've reached over 3,000 NRCS employees. If you're in the second tranche of states still waiting to do climate conversations, encourage your NRCS leadership to inquire about it and to reach out to Sarah Thompson and ask her, like, hey, when are you coming our way? example of science translation data synthesis. From those climate conversations that Sarah helped lead, what we kept hearing was, I wish that the climate information was more specific to my location, right? These big national reports are great, but we need more localized information. And so if you scan this QR code, it'll take you to a portal where you can get a one-page synthesis of what do we know about the climate trends in either your state or your county. Climate trends, which are summarized up in the top in blue. In the middle are some, how are temperatures and precipitation changing, like historically, depending on the season, which we know is important to agriculture. Down at the bottom, in the little table at the bottom, what are the top causes of loss in your county? Top causes of loss of insured crops. And this information comes from a really cool tool known as Ag Risk Viewer. So if you Google Ag Risk Viewer, it'll take you to a tool where you can dig into the RMA and FSA data to learn about the top causes of crop loss in your area. If I haven't interested yet in a resource, but you're wanting to learn more about climate change, this is a really great webinar series that USDA sponsored last year. It's a 12-part video series that was recorded and made available online. And so yeah, you can pick and choose from the 12 videos. The first one is just basic climate change 101 from NOAA. So it's just a great trusted resource. And then they move into more applied topics. How does climate change affect crops, animals? And then the 12th video is about people and bringing people into climate change. And I was lucky enough to get to participate in that one. All right, tools and tech. I know everybody loves tools and tech, so we can't go without saying a few things about this in the last minute. The freeze date tool. This comes from our Midwest Climate Hub region and the Midwest Regional Climate Services Center. Really cool tool for the Midwest. I wish we could get it expanded westward. Apparently frost freeze calculations become a little bit more complicated as you move into the arid West. But super cool for those living in the Midwest. You can go to this website. You can take a look at trends. So again, go to your county. I've selected Burleigh County, North Dakota here. Go to your county and you could take a look at what are the trends in the last spring freeze of the year in my county. How has that changed through time? What about the first fall freeze? Is that changing in my county historically? And then put them together for the growing season length and what's the trend there in my area. So for here in Burleigh County, went ahead and took a look, and on average, the growing season length has increased by about 4 days per decade. But you can go in and look and see on which end. Is that happening because of the spring, an earlier last spring freeze or a later first fall freeze? So a neat tool from them. I think in a few talks you're going to hear from Marina Skumenich from NOAA NIDIS. And I don't know if Marina will have time to talk about the NIDIS soil moisture dashboard, but this is a cool new experimental website where NIDIS has brought together several soil moisture sources that are using different methods, looking at different depths, all in one place. Go to one website. Go to one website, you can zoom into your area, and then you can just tab between CropCasma, GRACE, nationalsoilmoisture.com, all of these different sources, and your area will stay the same, and you can just tab between them and see what these different products are saying about your soil moisture. So I love that tool. My forest folks. This is coming from our Northern Forest Climate Hub. If you're interested in forested soils, they just put out this paper relatively recently asking how would soil carbon change if we were to harvest more or less in different areas. And as it turns out, it has a lot to do with soil type and the parent material underlying those forests. And so you can go and look at this GIS tool to see if timber harvest were to increase in an area, would we expect soil carbon to increase or decrease? And I'm almost out of time, but I have to give one last shout out from Ag Research Service, who houses us as a climate hub. You heard yesterday from Mark Liebig about the LTAR, Long-Term Agroecological Research Network. Again, quickly find, there's 18 sites across the country. Hopefully you have one near you somewhere. But LTAR is trying to make their data more available. So if you love data, you love analyzing data, I'd encourage you to go to their data inventory dashboard. The green sites represent croplands, the brown sites are rangelands, the blue are integrated. So you can go and see how many data sets does each site have, about what. And then because you're soil folks, they've made a soil attribute discovery tool. So there's an LTAR soils working group. If you go to this link, it'll take you directly to a searchable database so that you can see exactly what soils data are they collecting, how are they collecting it. Hopefully they're collecting it similarly across multiple sites, so you can do some cross-site analysis. And again, these are long-term agroecological research sites. So hopefully, if they don't already have long-term data, they are working up to it. So yeah, you guys are the experts. Go check out the soil attribute discovery tool. And let me know if you can see a way for us to partner moving forward. Thank you. And again, I'm sitting over here at the table in the front. I'll be here the rest of the week, so don't be shy. Thank you, Dr.
Hoffman. Our next speaker, you know, he gave us a short overview of the history of the exquisite lab across the river here. And so here we have Mark Liebig to discuss climate regulation services from the Northern Great Plains Agroecosystems Project.
Okay, all right. Thank you, Dave. All right, hey, well, hello again. I'm going to kind of continue on with sort of climate-related themes, but I'm going to kind of frame it in a local context. Focused very much on the research that we've been doing at the lab the last 20 years. I'm kind of like Dave. I got to set the table through context. I got to get that narrative squared away first. But then we're gonna dive into really 3 data tables that I'm going to share where we'll focus most of our time, and then take a step back and think about our agroecosystems perhaps in a broader context. So the issue is that we've got this carbon debt throughout the Great Plains. You can look at data sets from up in Canada all the way down to the southern plains. The effects of conversion have been significant, upwards of 40% carbon loss over time. It's about 1/5 of the total carbon look across the entire United States. So it's a pretty big hole to try to drag yourself out of. And what's interesting, at least at the research lab, is that you can practice no-till practices under continuous cropping for 40 years, and you're still going to have that debt. And what's interesting, the question about depth here I think is really good. You're seeing that the losses are very much concentrated in the top 30 centimeters, and very much really in the top 5, so the top 2 inches. We just have a hard time getting that carbon back to where it was previously. And the reason is that we've got this imbalance, right? I mean, the outputs have been greater than the inputs. There was initially the loss from erosion that Dave talked about, but we have increased mineralization. We're taking off grain, we're taking off residue. We're just out of balance here, and so it's no reason. It's a good reason why we're looking at all kinds of different options to try to figure out how to get this balance back, whether it's cover crops, or doing changes to our disturbance regimes, expanding the portfolio of our crops and our rotation so that they're more diverse, Perhaps taking another look at energy crops. You know, we did it in the early 2000s with switchgrass and others. Maybe we need to rethink that. Certainly soil amendments like biochar are in the mix as well, and I can't forget about our woody species. There's all kinds of options out there that could potentially be utilized and placed for success in a local context. But the thing is that it's not just about carbon. Certainly things here on the right hand of the slide are important. You know, getting that photosynthesis translocated into the ground through roots, that's where you're really going to build it. But there's these other sources of greenhouse gases that we have to take into consideration. All right? I mean, so there's certainly the CO2 emissions associated with farming operations. You got to take that into consideration, the inputs. But the real bugaboo is nitrous oxide and to a small extent methane, which fortunately for our part of the world, we're actually a methane sink for most of our production systems. Not a big one, but we are. So it's a broader picture. And the kick of the pants of this is that these gases are not really equivalent with respect to their capacity to be able to trap heat in the atmosphere. I'm sure you've heard about this. You know, methane and nitrous oxide are quite a bit stronger, especially nitrous oxide. I think that the analogy there, it's like garlic salt. A little bit goes a long ways. Yeah, that's an N2O. It can really trap a lot of heat. So when you look at a CO2 equivalent basis, they pack quite a punch. N2O being about 273 CO2 equivalents, and methane 27 based on a 100-year time horizon, and these are estimates from the scientists that put together the IPCC report, and that's using the latest updates since 2021. So it's important when you're talking about climate mitigation is to consider the full greenhouse gas balance, not just the carbon stocks, all right? And so that's where we've been, about the last 20 years through evaluations at the research lab, leveraging the long-term studies that we've had in place to track these things and see what stories we find. And we've done evaluations under sort of the rain-fed cropping systems. We've done a recent study looking at the integration of crops and livestock, and then one utilizing our long-term grazed pastures. And so I'll talk about each one of these. The first of which is our dryland cropping systems study. We did our evaluations this is actually a study that was established in 1994 by Don Tanaka. We did our evaluations on the gas fluxes between 2006 and 2009, looking at 3 cropping systems: a spring wheat fallow, a continuous spring wheat, then a spring wheat, safflower, rye. And the rye was like a cover crop. You didn't harvest it. Basically, it was designed to catch snow. That was its purpose. And so it was returned back to the soil as residue. Everything was no-till management, all right? And the way we measured our gas fluxes for the methane and nitrous oxide is these little chambers here that you see in the picture. So they're about PVC pipe. They have collars in the ground, and we would measure the gas fluxes by hand. Obviously, you've got to go out there with syringes and collect them. But we went the entire the year. So we just didn't do the growing season when it's comfortable, but we also were out there in the winter. And also during the early spring, which turns out to be really, really important if you want to capture N2O fluxes. Okay, so there's a lot of tables, a lot of figures in this paper. This is the one that really summarizes the story, I guess. And what you have there is that you got the 3 production systems, each have a column, and then you have the factors that contribute the CO2 equivalents to the overall net greenhouse gas balance. And so I'll draw your attention to the numbers for soil organic carbon change. What we're seeing here does not surprise us. Spring wheat fallow, slight loss under no-till, we'd expect that. The continuous spring wheat, it's a small sink. Not doing great, but it's a small sink. And that spring wheat safflower rye is actually doing a pretty good job. So just let me back up a little bit. If it's black, that means it's net CO2 going into the soil. If it's red, we're losing it, okay? So a negative sign means sort of a good thing from a standpoint of mitigating the greenhouse gases, okay? The kicker is that when you add all these up to get your net GWP, Two of them are sources. One is really strong, that continuous spring wheat, and it has everything to do with the fact that we're blowing off all this N2O. It's just not efficient at all in being able to utilize the fertilizer that's applied. And yeah, sure, the spring wheat safflower rye, it's minus 14, but that number is not different from 0. Okay, back to the drawing board there. We got to redesign our cropping systems to reduce this footprint. Let's move on. Our integrated crop livestock systems. This is what we actually just recently did with some money from NIFA, looking at a study that was also established by Don Tanaka in 1999, where we had grazed and ungrazed cropping systems. By the time we got around to it, the study was fairly robust. We were in our third phase of it, so there was a lot of good history there. We had good baseline samples. Everything again under no-till management. Same methodology on the gas fluxes, and we had a 15-year time step on the soil carbon change. I should mention, carbon change here for this study was measured down to the baseline samples that were reliable went down to 3 feet, so right around 90 centimeters, and that was the same case for the previous evaluation we did for the dryland cropping system. So we were going down with depth. All right, same type of data slide here. You can see all the factors there dealing with the CO2 inputs for the production, the field operations. This one's new because you got to take into account enteric fermentation, of course, because you have grazing cattle. But again, focus in on the soil carbon change. Hey, this is good. We're seeing a positive benefit from the standpoint of carbon stocks. We're changing over that 15-year time step. It's happening just at the near surface in that top 7.6 centimeters, but it's something we can detect. But look at that N2O flux. It essentially erases over 90% of the carbon that you're increasing over that time. And when you add everything else up, you're a source for both systems. Now, full disclaimer here, I made a little mistake on the enteric fermentations that wasn't caught during review. That number for enteric fermentations is quite a bit higher. And whenever my life slows down, I got to write the errata to let people know that number, it's even more challenging for us. The story doesn't change, it's just the hill we have to climb to make that sort of climate neutral is going to be tougher. All right, so last evaluation. Am I past my time all right? Do I have 9:30? Okay, sorry, all right, yeah, that's right, 9:30, okay, all right. So last evaluation, this is our long-term grazing systems that we have at the research lab. These were started by J.T. Service in 1916, and we have 2 of them that continue yet today, and so by the time I got here, it's like, well, that's one thing I want to measure because it's got great history. Same methodology on the gas fluxes. Oh, before I back up, we also had a third treatment, a crested wheatgrass pasture that was established in 1933. It's unique because it receives a little shot of fertilizer in the fall. You'll see this is really important because we want to boost the production of that biomass for grazing the following year. You're going to see the consequence of that here pretty soon. Here, for the soil, we went to our soil archive. So we went to samples that were collected by Russ Lorenz in 1959. He collected them down to 2 feet, and so we did equivalent thing in 2003. So a 44-year time step, which is not too shabby when you're looking at carbon change, but I think it underscores the value of having archives to be able to pull from. All right, similar type of table here. You got the 3 practices across the top. You got the variables there over in the left-hand column there. And so, draw your attention to soil organic carbon change. Hey, we're a good, strong carbon sink, which that's what we would expect. And this is actually, the rates really match very well with the rates that Al Frank measured using sort of Bowen ratio real-time measurements over about 6 years. And so that was really good, but look what happens with that application of fertilizer in the crested wheatgrass and those N2O emissions. It's incredible how much comes off, and the surprising thing is, half of that happened between the months of December and February. because midwinter thaws, you get these what they call hot moments. And so underscores the importance of measuring these gases throughout the entire year and not just when it's sort of, comfortable to do so. Yeah, so net GWP, here this is one instance where we have some production systems that are net greenhouse gas balanced on, have a positive story associated with them. And even though the moderately grazed and the heavily grazed are not different, if you put that on sort of like a greenhouse gas intensity basis, meaning like the kilograms of beef produced, they do separate out statistically, so you actually end up sequestering sort of more net greenhouse gases under a less intensive grazing regime compared to heavy grazing. All right, so in summary, our dryland cropping systems are greenhouse gas source or neutral, our integrated systems are sources, our greenhouse gas sinks under grazed native pasture can be sinks. And so it shows where we need to do our work yet on this whole issue, and it has a lot to do with focusing on our cropping systems. And we're continuing to do that with our research, and hopefully you'll get to see some of that tomorrow. We also are doing, to complement this, we're also making micrometeorological assessments. So this is using eddy covariance technology. This is a whole story unto itself, and I'm going to leave it until tomorrow. My colleague, Nick Saliendra, very much leads these efforts, and he's going to have part of the field tour. He's going to talk about some of the results that we've seen under hayed pasture, and then a sort of a business as usual corn, soybean, wheat rotation. So we'll review that tomorrow. But this has got me really thinking about, considering climate regulation service maybe under sort of a broader context and looking at other ecosystem services, especially those that may relate to soil health, which I'll get to here in a second. Here's an example just from perennials, a paper here from Richter. It shows all the things that perennials can do on the landscape, which all of you realize this is the case. And the regulation of the chemical composition of the atmosphere is just one of many services that are provided, okay? The other thing has to do with what resonates with producers. There was a really good study that was done by Arbuckle at Iowa State University in 2015. It was published then. It sort of aligns with sort of the experience that I've had with producers, where if you talk about, climate preparedness in the context of how can you, change your practice to adapt the crazy weather that we're having, that kind of resonates a whole lot better than, well, let's mitigate our greenhouse gas emissions from your fields. Like, well, things get a little quiet at that point. And so what that says is that there's a way to maybe reflect upon our mitigation goals in the context of maybe sort of a soil health rubric. And I really like these soil health principles that the folks at the Minokan Farm put together over a decade ago, because what you can do is that you can take each of them and then you can sort of slide in the carbon inputs and outputs into the narrative and maybe guide people that way, right? And what's exciting about this is that there's no lack of meta-analyses that have been done in the last 20 years that show the benefits of these practices on all kinds of different soil properties that improve soil function. Here's just some examples of soil armor and minimizing soil disturbance. It goes on plant diversity. There's things we can do from the standpoint of improving soil biological habitat, fertility, and so forth. The continual live root is a big one because that's perennials, right? So there's all kinds of things that can benefit from the standpoint of structural attributes, improving structure, erosion risk, also increasing that nutrient retention, which we've observed in our own research at the lab, and improving soil microbial diversity. So there's a lot of benefits from that. I think that probably resonate perhaps a little bit better, and maybe we'll be able to also increase those carbon stocks and minimize N2O at the same time, perhaps. So it all goes together to support you know, sort of the broader collective effort that we have in terms of making our agro-ecosystems sort of achieving multiple ecosystem services instead of just focusing on perhaps one or two. So that's, yeah, that's my story. I do, though, want to take time to acknowledge the people that really made those 3 data slides possible. For those of you who are familiar with this type of work, you know how labor intensive it is, and especially trying to convince people that they should go out in February and gas sample with me. Yeah, and so it's been an amazing crew over the years that I've been really privileged to be able to work with, and they're all you know, mentioned here. Not to mention also all my colleagues at the lab that have to tolerate me. So yeah. So hey, that's my story. Thanks for your attention. I don't know if we want to take a time for a question, or this is going into a break, so we can just yeah, okay.
Quick reminder that if you have a poster, you need to bring it over to room 432 before noon. Those of you that were in the Subaqueous Soils Committee yesterday, you're supposed to meet in the southwest corner of the room over here so that you can vote for a new chair.
Folks, we're going to begin the next session. If you could gather back at your seats. Folks, gather back at your seats. We're going to begin the second session. Good morning again. We're going to begin this session again. Our next speaker is Dr. Marina Skuhanic. She's out of Boulder, Colorado. I think she works in the building that we used to play around when we were kids, NCAR we called it then. So at any rate, she'll be talking about National Coordinated Soil Moisture Networks, which is going to be quite resonant with most of this audience. So we're thrilled to have her on board. And here we have it.
Right, you're going, Marina.
Okay, well, good morning, everybody. And I have to say, I would be honored to be a doctor. I've only got a master's, but anyway, hopefully I still know a few things and can represent our program well. Sorry I couldn't be there in person. Just want to take a little time to talk about this National Coordinated Soil Moisture Monitoring Network, what it is, and why soil characterization is key to our success. Next slide. Okay, NCSMMN is our acronym, very unwieldy, but we got the name from Congress. It is an effort to deliver coordinated, high-quality, nationwide soil moisture information for the public good, and that public good is very broad. I come from NIDIS, the National Integrated Drought Information System, so focusing on drought issues, but we want to attend to all of the ways that soil moisture can inform public decision-making, from drought to flooding, agricultural monitoring, fire, health issues, et cetera. And the list is kind of expanding as we go forward. But our aim is to build that information system for the public good, and we do that through three primary activities. The first, build a network of networks, drawing off the data that already is being collected by a number of federal and state mesoNets, soil moisture data along with atmospheric data. And then building more mesoNets as time goes by, and blending that with information from other networks like research or private soil moisture monitoring networks, and then ultimately including satellite and model-based data, with the idea that we need the broadest range of data to get accurate pictures of soil moisture conditions. We also want to build a network of people, so that's our community of practice, acknowledging that if we can connect people from the data providers through the researchers to the climate service professionals to end users, farmers, water managers, we'll have the strongest initiative and make sure that we can share across with each other and build the best products. And then finally, to deliver those products, we really need R&D. Representing soil moisture is complicated. Maybe representing any natural phenomena is complicated, but soil moisture is particularly so, as I'm sure you all are aware. It's not enough to know what the water level is in the soil. You got to know more about the soil to really interpret it. Next slide. This is just to give you a quick sense of the distribution of soil moisture networks around the country. This is not all of the networks currently in operation, but it is most of them. And as you can see, there are some areas that are quite well resourced. A couple states, Oklahoma and New York, have really put an effort into soil moisture monitoring, and then others that are not so well resourced. So of course, those are on our sites to help either through federal or state or other ways build those resources. Next slide. So when we say we want to deliver soil moisture information, what are we talking about? Well, our ultimate aim, or sort of what is it called, the golden fleece, is to build these real-time gridded soil moisture products that will serve public decision-making, that blend the three streams of data, in situ, remote sensed, and modeled outputs. And we call those the three legs of our stool. That gives us that stable platform that we can build products off of, because each data stream has its own benefits and areas where it doesn't work as well. But in addition to those products, we also want to make sure we're delivering information all along the data pipeline. So thinking about the data providers, we're really focused on some technical assistance development. We also want to build standards for data quality. What do we mean when we're talking about high quality data for the public good? What's the criteria for that? There aren't really sensor performance standards. We need to get some level playing field in terms of comparing sensors. So we're focusing on that. And then we're wanting to build data sets for research and tool development. So even the raw data, of course, is a product because that's what's used by the research to then build the ultimate products from that. And then in terms of data fields, we talk about soil moisture, but it's also the case that we're going to be focused on getting soil temperature, particularly in northern areas where that makes a difference in terms of interpreting whether whether the ground is frozen will affect, the soil moisture reading. But in addition, the metadata we consider essential to our effort here. We need to know more than just what is the level of water in the soil. We need to know soil type, soil characterization. Beyond that, we need to know other things, the kind of sensor, et cetera, but metadata is an essential part of what we do. And again, soil characterization is an essential part of the metadata. Next slide. Just want to give you a quick sense of the executive committee. This is a group of people that have been organizing since 2010, not all of these people, but a volunteer effort started since 2010 to organize some kind of national initiative. It has now grown to this executive committee, which is, other than myself, everybody's volunteering their time to help build this initiative, our path forward. And you can see there's just a range of organizations, federal, university, et cetera. So next slide, please. So that committee has started in 2019 to actually respond to a congressional directive to build a strategy for this national initiatives. So working through that, we have this strategy published in 2021 and approved by the NOAA leadership to guide our efforts as we go forward. And so I've got the key recommendations here, and then the font in gold is the connection again to the soil community. So first recommendation, formalize and expand partnerships. We're really focused on making sure we take advantage of all the different activities, different mesonettes generating data, but also the soil survey community is a key partner. And we have a very, at this point, ad hoc relationship that we want to formalize over time. We want to expand in-situ soil moisture monitoring. I mentioned that earlier. We want to develop data quality criteria, including the metadata. And again, this includes very much the soil characterization. We want to support research to develop these methodologies and products. And there's a whole range of issues. How do you interpolate layers, measurements over layers? How do you interpolate spatially? How do you blend with satellite and in situ, et cetera? But again, one of the big things is how do we factor in soil information? We know certain things, plant available water, but what else can and should we be doing with soil information to have better methodologies to represent the conditions? Emphasizing communication and outreach, which of course is what I'm doing with you all now. So that's, I should have a little yellow or gold thing on that bullet as well. And then finally developing these products that I mentioned. And as I said, plant available water, very critical. Making the difference of, how is this going to affect plants, not just agriculture, although that's a huge one, but also ecological conditions, et cetera. Next slide. So these are our priorities, which track with what you've just heard me saying. So I won't spend a lot of time here. We want to increase monitoring in undisturbed areas. We want to increase it overall, but we're particularly targeting forest and tribal lands as two areas that are really undisturbed at this point. Again, developing the technical assistance for the in-situ networks. In terms of data delivery and application, this first bullet, develop a curated product kiosk. We're realizing that even as we want to build newer and better products, there are a lot out there already, and a lot of users have said to us that they just would like a little bit better roadmap to the existing products. Could we help curate them and explain their areas where they work well, et cetera? So that's a target of ours. We're looking into the soil moisture and wildfire nexus, recognizing that soil moisture conditions can really be a good early warning indicator of wildfire. We have this data value study. It's in the upper Missouri River Basin, which is looking at not quantifying so much, but characterizing and quantifying where we can the value of soil moisture data to affect decision making. and then wanting to particularly target the mapping needs of the U.S. Drought Monitor authors, because again, their work is so important, because such consequences for farmers and ranchers that and others that we want to do a better job of giving them resources. And then finally, we've got our community building and engagement. Okay, next slide. And I've just got two more. So activities that intersect specifically with your all activities, your all work. Again, the project in the Upper Missouri River Basin, the Corps of Engineers is managing a 540 station build out of new soil moisture and state-of-the-art soil moisture and snowpack sensors. And you all may know this, but if not, you should know that NRCS is a critical component of that. They're doing their quality soil characterization for each of those stations. So that area on the Upper Missouri River Basin is this beautiful test case for what a high quality state-of-the-art system can deliver in terms of information. And so then, as I mentioned, this data value study is a tag on to that build out with NIDIS leading that. That's our effort, again, an interagency effort to sort of document how that build out and with the quality that we're getting can make a difference. We're in the process this year of finalizing two guidance documents, which I believe those of you may or may not have heard about. I'm happy to, if anyone's interested in participating and seeing what's being described in terms of soil characterization, it would be great to have your participation. But we've got one on data quality overall, what is the data? How do we know that we have high quality data? And then a companion piece, which is what specifically is the metadata that should be included. Now that one, of course, again, very much speaks to what are the soil characterization parameters that we should be targeting. I'm going to put my email in the chat. So if anybody's interested in learning more about any of these things, but specifically that wants to participate, really would love that. We've got a couple of workshops coming up. We're pretty excited about these. July 25th, which is that like next week, 2 weeks from now, we're going to be doing a field workshop with existing Mesonet operators, sort of peer-to-peer sharing to again build the capacity, build the knowledge base. And then in August, we have a annual soil moisture workshop, but in particular, we're going to have a field school for researchers, early career professionals, well, actually anybody, but the target is a little bit more of an introduction, again, a field-based introduction to soil moisture monitoring, which again will include discussion about soil characterization. The last two, I just want to mention to you, we've got a listserv, and I will put the link to join that in the chat, probably after I'm talking, because it's a little hard to multitask. But if anyone wants just to stay up, we don't send out a lot of emails, but it's just keeping people apprised of what the activities are of the NCS MMN or other soil moisture related activities. But also we run a seminar series, and it occurred to me, I would love to get a soil survey presentation. So I'll follow up with Wade, but others too, if you are interested in a 15-minute talk. We do these quarterly about soil survey, so the effort that would be very valuable. All right, my last slide. Next slide, please. All right, the bottom line, this is a quick one. So this is just how it all adds up. We all of us need better early warning for natural hazards like drought, flooding, and fire, et cetera. Soil moisture is a critical early warning indicator. It's very clearly understood as that. But soil moisture levels must be interpreted to have meaning. It's not enough to know that it's whatever it is, 30%. So soil characteristics are key to that interpretation. What does saturated mean? Depends on the soil. What is plant available water? Depends on the soil. And other physical and ecological conditions also depend on the soils. So 1, 2, 3, and 4 equal the bottom line, which is that your work is key to our success, and really very much appreciated. Okay. I do actually have one more slide. So one of the next slides is my thank you slide. Okay, thank you. And I think there's some problem with me hearing your questions, but if anyone has any questions, I'll go ahead and pop them in the chat. And meanwhile, I'll add a few things here. My email. And then link to the listserv.
Excuse me. Mic's working.
I'm kind of big. I'm going to wave at myself.
Thank you, Marina. Very,
Okay.
very exciting news.
So I can't
Questions
hear a
that could,
thing.
Jade,
Oh.
can you hear me?
How about now we're going to echo. Are there questions for Marina?
Are there questions or comments regarding this really pretty inspiring talk? Here we go.
Hi there. So earlier we saw from one of the other presenters sort of a comparison of the different predictive methods for spatially mapping out like soil moisture using, I can't remember, you know, linking it with like the SHMAP satellite and things like that. And then I saw like a leaky bucket and like a variety of different like ways to, you know, spatially display that information. Is there any consensus on which of those is maybe preferable, or you know how they compare or complement one another? Do you know much about that?
So the question came in and out. The sound came in and out for me, but if I understood the question, it was discussing or mentioning there were a couple different ways to interpolate the data, and if there was any consensus about the best way to do that, and the answer is no. I mean, there's obviously strong opinions, and so I think if Steve Inquiring from OSU were here, he might tell you that there is there is a consensus, but my sense of it is that that's still a TBD. That's one of those research things, and I am not a hydrologist or a PhD scientist, but I think that it's pretty clear that we do need to put some effort into that, and that there might be more than one way to do it, depending on what you need to prioritize, what you need to emphasize. So I hope that answers your question.
Thank you.
Other questions?
I know they posted some links, the virtual people. I was wondering how us as the audience, basically, can we get those two addresses? Can they be emailed out, or I know they popped up on the screen, but I would love
Thank
to have.
you. That is so funny. Since I'm virtual, I'm just giving you virtual links. I'm happy to send something to Wade. There'll probably be some material sent out after the event, and so I'm happy to. I'll send I have a Word file with links that I can send out.
That would be good.
You showed a map that had all the soil moisture stations. Could you have a map that would put the land use at those stations at the same time? So some ag, some forest, some urban land, things like that.
Okay, I apologize. You're asking about the map I showed of the different networks, and you were asking if we know what the land use is for how many of the stations we have land use for?
Yes. Just for example, what percentage is ag? What percentage is forest? Any idea?
Sorry, the audio is cutting out for me. But if it's a question of what the land categories are for each of those stations, I think we don't have anything easily documented. I do think, though, that we could probably, each of the networks probably do that kind of characterization themselves, or many of them at least. So this is an opportunity, and thank you for raising that question, and that's something I'll put on our list. We should be able to. I know that there's generally understood that the focus is really agricultural lands, although in most cases, right adjacent to the agricultural land because of the effects on the sensors for having activity above them. So, but what the percentage is and et cetera, I don't know that. So I will check on that.
I think we have time for another question or comment.
this is more of a comment than a question, but someone was just asking about, where these stations are located. And most of them are in agricultural land. I'm John Kabrick. I'm at the Northern Research Station, the Forest Service. And we're very, very interested in getting forests instrumented so that we have this kind of information. It's essential to what we do for our management. It's essential for any kind of activity we do in the forests. And so this is, to me, this is a real opportunity for us to work together in partnership with NRCS, Forest Service, and other entities, state people, to get a lot of these sites instrumented so that we can begin to test these various models that you guys are asking questions about, develop new approaches for modeling in real time soil moisture. But I can assure you there's a lot of interest in this across the country.
Thank you. Thank you, Marina. We'll close out questions.
All right, thank you, Marina. We'll let you go.
Okay, well, thanks everybody. Really, really appreciate it. Bye-bye.
Okay, and our next speaker is Sky Wills from Lincoln, from the KSSL. So.
All right. Not KSSL. It's a whole center. We don't all do lab work. It's okay.
Well, it's my KSSL.
All right, so we should all feel really important. We've heard about, soil moisture and carbon, and soil scientists are important for all of it. And the speakers we had this morning set me up really well for what I want to talk about. So I'm going to talk about the Science of Soil Health initiative that we've been working on the past several years, and a particular implementation of that we call DSP for Soil Health. So the Science of Soil Health was set up to test the things that NRCS says we want to do. So we have somebody mentioned early on that we have these fundamentals of soil health, and then there's some certain ways that we promoted for ways to measure that. And so we're trying to combine what has been promoted and this technical document, which I'll get to later, but this is the ways that NRCS has said this is how we'll measure soil health. And then we wanted to combine that with the ways that we measure dynamic soil properties and soil surveys. So we have this set of cooperative agreements all over the country, because we know, we're soil scientists, the first answer of any soil science question should be what? It depends. It always depends. And so we know soil health metrics are no different, right? So we set up this common set of experiments around the country with a similar set of parameters. We combine soil survey, dynamic soil property protocols, and these soil health protocols. So the goals of this were to develop reference values, right? We want to know what we should be getting for soil health, because I know what a pH of 7 means, but I still am not real sure what beta-glucosidase values mean. I have to think about it. And I don't know how they differ around the country, so we need to set these things up. We want to assess the usefulness. So maybe some of these soil health metrics are only good for certain locations. We know that, and a lot of us do know, we don't use that here. It doesn't make any sense, but we don't have a documented set of instructions for where things make sense and where they don't make sense. And then we want to, populate our soil survey databases. We keep a lot of data. We have a central repository. We can share that with other people and make use of it. And then finally, we want to compare different cooperators measuring the same kind of things we might measure at KSSL. Like, are they repeatable? Do we get the same answers? How much is lab variability? So we measured all these metrics. These are pretty small. You probably can't tell what they all are, but that's okay. The idea is there's a lot of them. And we're measuring some general things like a basic PEDON description. That matches it up with what we do for soil survey. And then we're going to look at soil structure. We're going to look at some soil biology, and then our general characteristics. And so we did these all according to that tech note. So it's all the same method, it should be the same procedure. And I'll get to that in a little bit. It wasn't quite that simple, but that was the idea. That was the goal. So the general outcome is that we were able to have the same things measured all across the country. So we could know both with depth, because we went to a meter, which is a compromise between those of you who would like to go to 6 meters and those of you who would like 30 centimeters, right? So we went to a meter for soil carbon, that's usually plenty, but then we can also look at things like just at the surface. What should I see if I take a soil health sample? So I'm gonna go through a few of those results. I'm not gonna talk about this in detail because the thing I wanna bring up is that you mentioned, I think John mentioned this, that business as usual. So if we go to compare each of these soil series across the country, we don't have a common way of thinking, especially in agricultural systems. What is our benchmark? What are we comparing to? What is the goal? We use a reference state that intersects, and I didn't think to put a state and transition model up here, and I think I probably should have, but we intersect a reference condition with that state and transition model. So that's something soil survey, that's something NRCS already does. So we want to know what within a reference condition, or as near as we can find it, what are those values? Then we want to think, what's business as usual? Business as usual, different everywhere. And as was mentioned earlier, it actually can change with time, right? What we do today is not going to be what we do tomorrow. But for right now, business as usual, you know, think of your standard. It's not exactly conventional agriculture because in a lot of places, there's a lot of conservation being done. So we want to think about what's the typical level of conservation done in this area. And then we have a soil health management system. These are best practices like cover crops, no-till, things that we think should improve the metrics that we're measuring. So we can start to look at this different soils, looking at the surface only because it gets a little overwhelming if we go very much below the surface. And this is where we see the changes the fastest, of course, right? You know, things turn over at the top first. So it very much matters which soil you're looking at. It very much matters if, I have to look at the soil names because I don't even remember, but Cecil, it's a classic southeastern soil, right? You're gonna get totally different values than you might get in, say, the Palouse soil, which is in eastern Washington. Very different values, very different levels, both for the reference and the bottom. Like in some places, you might have 2% carbon, and that is the best you are ever gonna do. And then in other places, as we heard this morning, it's really, that's a degraded state. That's something different. And so what the overall value is almost meaningless if you don't have something to compare it to. So we can really start to drill into a few of these soils and a few of these conditions, and we can start to think about, okay, what's the reference state? If I go take my own sample, where am I on this? Can I get better than this? Or would I have to do a wholesale conversion? In this case, the Key Soil Series, which is in western Kansas, it's pretty dry. There are short grass prairies still being grazed. They have pretty high levels, but it didn't seem to matter whether you were in business as usual or soil health management system. And honestly, I think that's because business as usual was pretty good. They were, I mean, it blows. It was mostly, I mean, what we call conservation or reduced tillage. It was, they were not plowing things over in November. They were doing a good job. So our preliminary results, for that, it's soil dependent. That is the take home. For our lab comparisons, we saw that with some things that are pretty standardized, such as soil organic carbon through combustion, it didn't really matter what lab did it. It was very standardized. Now, if you do loss on ignition, it's totally different. This is a combustion, very controlled environment. However, permanganate oxidizable carbon, soup to nuts, man. Some people were pretty comparable, some people were pretty crazy, and you can see on this graph, there's just like, these populations don't even look like the same thing. And we went back and corrected these values as best we could, and it still looks like this. So that method has some, well, we're gonna say issues. Now I don't think that means that we should totally throw the method out, but I think we should be very careful in how we apply it and what it means and what it's for. So I'm going to tell you a few details just as an example of this from black soils, which Stephen really helpfully introduced this morning. So black soils they're kind of analogous to mollisols. They're just deep, dark soils. And it's a classification. We were doing it for something else. And so I thought, hey, I've got a couple of soils that actually fit this. So let's look if these two soils are the same. So we're going to use these examples. We've got the Keith soil that I mentioned in western Kansas. It's aeritic RGS pretty dry, less derived, your standard, high plains kind of soil. So if we put these soil colors up here, you can see that these are pretty nice and dark all the way down, but the really dark stuff is really just at the surface. But there's not a ton of difference between the different management systems. The Palouse soil, however, which is in an Ultic happily 0. So this is in a xeric moisture regime in Washington. These soils, well, there were some differences, but not too dramatic. Mostly it was mixed up. And to a meter, it's dark all the way down. This stuff has been churned over so much that it isn't really that different. Although there may be a caveat to this, and I'll come to that in a minute. So if we look at the individual properties for these, we can see, as we expect, reference condition always comes out on top. Business unusual versus soil health management systems are pretty variable. There's no consistent pattern, and this really is similar to what we see across other soils as well. There's nothing in here that tells me, okay, this does or does not work or is not useful. So what I do to put this in context and think about this in terms that maybe could be useful for a soil survey user or maybe could be useful in a DSP context. And that is to think about these in relative terms. So if instead of having a state and transition model, maybe we have something where we say business as usual and soil health management system, this is the best I can do with the crop production system. The reference condition is probably the best I can do, period. And so maybe I need 2 different levels to have said anything about this. And the Keith soil ends up being a little different than the Palouse soil, mostly because of those reference conditions. Well, here's a little caveat to that story. So the reference conditions in Palouse were perennial. We couldn't find but one singular location where we could get a pit where they had not plowed. Because if anybody been to the Palouse in Washington, it is, man, they've got some crazy tractors, right? They're just like up and down and they're going for it. And sometimes they're a little what they call eyebrows where they don't plow, but there aren't very many of them. However, we found one. And at that one site, it was way up here. So that maybe this is really what the true reference value for this soil is, and maybe that's what we should be comparing things to. So we have another tool that we've been developing. You guys may have seen this paper, the shape curves we call them, and we're trying to implement this a little more broadly, but essentially we're going to create these curves based on all the data we've gathered this far. And so instead of having these upper limits or whisker and bar plots. Well, I love a box plot. I don't know about you guys, but when you show those to people who do not love box plots, man, they really don't love box plots. So we need something else to show people. And so we kind of compare it to like when you take a standardized test and you're in the 99th percentile. So sometimes you're in the 99th percentile, maybe you're 50%, or that gives you some idea of where you land. And so we're continuing to populate data, but we have a lot of soil carbon data, so we can put what we've done this far into it. So the Keith soil, man, these were all just kind of like stacked right on top of each other, right? So the soil health management system, business as usual, not great. Reference condition, that's 99%. So you have an idea, if you take a sample, you could plot yourself on this graph, or we have a handy little app that you put it in, and it tells you where you fall. For Washington State and Palouse, it's kind of the opposite, where the soil health management system actually got you pretty close to what you would get for a reference state. So maybe that is attainable for these systems, and maybe there is a different benchmark we should be shooting for. So it's just a different way of looking at the same kinds of data, but I think it's important we talk about how to communicate this. Like, what are we gonna tell people? What are they gonna do with this data? So I kind of buried the lead in here a little bit because lessons learned. The first one is the existing protocols were not good. We couldn't, part of the epoxy problem, part of aggregate stability, the protocols were not written well. So that has actually been retired. Whoops. We are not going to do that anymore. There's supposed to be a little box that says retired on here. I don't know what happened to it. So there will be simplified methods. There will just be a few things that we measure everywhere. So while we're continuing to do some DSP for soil health projects in Tennessee and some other places, the Science of Soil Health Initiative will back off of all of those methods somewhat. So it'll just be, instead of that big list I showed you, it'll just be a few, which in some ways makes it easier to manage, but in other ways will mean that it's not gonna be complete and some people won't be happy with it. So the standardized data, we can put them into those shape curves. Our researchers at their institutions are really interested in using the data we have. The data infrastructure we have is inadequate for this. We need to build some new stuff, right? I mean, not all of you use NRCS, but enough of you do to know that this is, I don't even know how we would do this, right? We've got new stuff. So we're working on it, but we're not there, and IT development is slow. And by the time we figure out what we want, we'll have moved on to something else. So we have to figure out how to do that. And then grouping these general conditions, though, that really seems to work well. And I mean, it's no surprise. The LTAR network, others have done this business as usual idea in the past. There's no reason that we can't adopt their language. It's something that people understand. It's something that we can communicate both within the scientific community, across scientific communities, and to our producers. And we think that this reference condition is the bridge between what we are doing in the world of DSP and soil health and what the rest of NRCS, all kinds of land managers are using in state and transition models. So updates. Oh, maybe this is where I put the box. Oh yeah, we retired that. That's going away. So no more soil health tech note. Any of you who have used it will probably be happy to hear that. The new SEMA 216, which is based on KSSL methods, I'm gonna predict that we will have to do some additional methods because those are pretty standard and they're based on air-dried samples and blah. I mean, it's just not everybody's gonna be happy, but it's a good start. They're repeatable, they're understood methods, we have lots of data, so let's start there. And then we're cooperating with ARS to do a whole bunch more sampling of those methods and a few others across the country so that we can build better curves, we can build better boxes, all of that. And then finally, we are kind of starting some new research with the SHAPE tool to actually think about forecasting climate change. So not just what are existing conditions, but what do we think the conditions will be in 5 or 10 years. So that is all I have. I want to put the cooperating institutions up here because there's a bunch of them and there will be even more the next time I share this. It took a lot of people to work through these and to figure out why it doesn't work in some places and it does others. And it is like the epitome of what NCSS and cooperative research can do. So we got a lot of people working on this. So with that, I might have a minute for questions, but I'm happy to talk to anybody about this later. Thanks.
Sky's going to be around, obviously, so you can ask questions of Sky through the afternoon, if you will. Our next speaker is Nick Jelinski. who is at the Tueday NSF station up in Alaska. Poor kid. And so he's going to talk to us about urban soils, and so hopefully that's going to come through virtually in just a moment. So Nick, you're up. Okay, thanks, folks.
Ready for you, Nick. Ready to go? Okay, can you hear me? Yes.
Yes, we can.
And you can see my screen. Okay. I will share here. Okay. Hopefully I'm good to go here. Thank you for allowing me to do this remotely, virtually. I know it's always a challenge. When Dave reached out to me, I wanted to try to make it. I was supposed to be in Alaska yesterday, but my flight got delayed. So I'm actually leaving in a few hours this afternoon. And originally I had talked about gellisols, but the organizers requested actually something about some urban soil work that we've done over the last 4 or 5 years in the Twin Cities metropolitan area. So I'm going to talk a little bit about that work. Our campus here at the University of Minnesota is in St. Paul. So we are in the middle of, we're one of the only land grants, maybe besides Ohio State and Hawaii Manoa, that's in a large metropolitan area. And so I've had some folks in my group that have done some urban soils work as part of a small part of some other projects. And we've got some data that's hot off the press. So I'd like to sort of put that into perspective and show you what we've been doing. A little bit of background about the Twin Cities, Minneapolis and St. Paul. So this is a land cover map of both city boundaries, municipal boundaries, showing building footprints, impervious surfaces, green space, and water. The Mississippi River runs through Minneapolis, and the Minnesota River comes up from the south, and they join and become the upper Mississippi as it flows through St. Paul. Minneapolis-St. Paul proper is about over 800,000 people in terms of population. The greater metro area itself, which is a 7-county metro, is more than 3 million people. And Minneapolis, the downtown is much larger in Minneapolis. It has the largest extent of concentrated urbanized lands. St. Paul, the downtown's smaller, more compact, but St. Paul also has some large industrial zones that are outside of the city center. The superficial geology, so there's been quite a bit of good glacial geologic mapping, superficial geology mapping in this part of Minnesota. So we know quite a bit about, in theory, the parent materials. Most of Minneapolis and St. Paul is dominated by outwash and alluvium. There's a large number of terraces of different ages, both the Mississippi and the Minnesota River. And then the uplands, there's some large outwash plains, and then there's some areas of till, sort of moraines of 2 different provenances. So one group of till that came from the northwest, one from the northeast. So that's sort of the natural setting. The other interesting thing about the Twin Cities is that the reason that we have 2 cities right next to each other that are less than 10 miles apart is really due to glacial and environmental happenstance. So St. Paul, you might be able to see it from this LiDAR image here, but basically there's an outwash channel that cut through a moraine that emptied out into the upper Mississippi, and it created this flat area here, which is called Lower Town. It's just from downtown St. Paul, and that's basically where the Port of St. Paul developed around. The Port of St. Paul is basically right here. So initially anyway, the St. Paul was a good place for barges to be unloaded. And so the Port of St. Paul developed here, downtown developed around the port. And then Minneapolis really developed around a place called St. Anthony Falls, which was used for hydropower, milling, et cetera. So that's why we have 2 downtowns that are so close to each other. But generally speaking, you can see these flat outwash plains and some hummocky areas of till. If we look at what is currently in the soil survey for Minneapolis, St. Paul, so this is not an updated urban survey, certainly, but there are a few good non-urban components that have been populated in some of these areas. And so those show basically what we would expect to see here under a natural setting, which is essentially mollisols and alpha sols. We're right in the prairie forest boundary here in this part of Minnesota. And so we have typically mollisols to our west and alpha sols to our north and east. So the big overarching theme of the data I'll show you is sort of trying to understand how key soil properties vary across Minneapolis-St. Paul by land use and land cover, with a special emphasis on the impacts of urban food production. And this is because a lot of the work that I'm going to show you is basically opportunistic. We've been doing this in small parts of larger studies that that other folks have had, that maybe not soils focused studies, but wherever possible, we've just been trying to opportunistically sample soils in a supported way. And so these are part of a larger project on distributed urban agriculture and food systems and community engaged research on urban ag practices in Minneapolis-St. Paul. And there's also an interest in evaluating urban agriculture, urban food production as a viable green infrastructure strategy. So that is something that policymakers in Minneapolis have been looking at for a while. The question is, how does urban food production in terms of soil characteristics compare to other land cover or land use categories in our metro area? So opportunistically, over the last 5 years, we've sampled soils at about 100 sites across Minneapolis and St. Paul. A number of students in my group have been working on this over the summer. And basically, the major land use land cover categories are community gardens and urban farms, residential properties, parks and green spaces. And then within each of those 100 sites, we established 3 sampling plots, about 2 meter by 2 meter plots, where we took a core. So these are 1 to 2 inch cores. We're not digging pits, very difficult to do in urban environments, unless we happen to have a foundation that's open or something like that, in which case we would actually describe a soil in profile. But most of the time we're taking cores. And we're looking at specifically organic carbon, phosphorus, available and total phosphorus, pH, a lot of other things like texture, nitrate, things like that, and to a depth of 1 meter. And so instead of doing morphological descriptions, what we've actually been doing here is define depth increments. So 0 to 10, 10 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100, down to a meter. So each of those plots has a core down to a meter, and then there's 3 plots per site. Additionally, we've measured saturated hydraulic conductivity using amosimeters in the very top depth increment and triplicate measurements per plot. And these sites were selected mostly based on access and permissions. You know, I hadn't done any urban soils work before I started my position here in 2015, and learned a lot about the difficulties of doing soils work in an urban environment. And so, you know, access and permissions are huge. Obviously, Digger's Hotline, all these things come into account. So we did our best to stratify across spatial and different land use categories. And then within sites, those 3 plots were selected to represent a range of management or land cover within those sites. And if a food producing area was present, we specifically did sample that. So what we ended up with over the last 5 years, from 2018 to 2022, are 132 sites across Minneapolis and St. Paul. I'm showing them here on the right. There's 3 plots per site, or 3 cores per site, so about 396 plots and cores, over 1,000 KSAT measurements, over 2,000 soil samples to that depth of a meter. And the breakdown is about 40 community gardens and urban farms, where we sampled turfgrass lawn and food producing and non-food producing areas. Parks and green spaces, about just over 30 of those, turfgrass lawn and natural vegetation. And then residential properties, about 60 turfgrass lawn and food producing and non-food producing or ornamental horticultural garden spaces in residential areas. So a lot of the data that I'm showing you, even though we were collecting these samples over the last 5 years, sometimes we've been slowly accumulating this data. So a lot of this data is hot off the press. And so what I did is I collapsed some of our land use categories into 5 for the purposes of the presentation. So turfgrass and or lawn, natural vegetation, including any unmaintained wetland, forest, or prairie, regardless of if it was native or non-native plants, but mainly just unmaintained vegetation. Gardens that are non-food producing, so again, horticultural or ornamental gardens, and then 2 food producing gardens, raised bed or in-ground, where literally just growing right in whatever media, soil media is on the top. So I'll show you some data here. This is KSAT in the top increment, top depth increment by land use. So the letters on the box plot signify significant differences between those types by Tukey's HSD. So any letters that are different are significantly different at a P of like 0.05 or less. So essentially with KSAT, there's a lot of variability. That's not surprising. But raised beds, again, not surprising, do have significantly higher surface KSAT than other land use categories. Gardens, both food and non-food producing, were not significantly different from turf grass or natural vegetation. So really the only interesting thing here is that raised beds had higher KSAT. Again, most raised beds are filled with compost or some low bulk density topsoil material, so not surprising there. And that essentially converting or having a food producing area does not decrease KSAT relative to turf grass, lawn, or natural vegetation. Surface carbons, this is organic carbon percent, significantly higher in food producing areas. So both raised beds and in-ground food producing areas, that surface increment 0 to 10 centimeter carbon is significantly higher than non-food producing gardens, natural vegetation, and turf grass or lawn. Again, probably not that surprising because people do really intensive inputs, especially in urban food production, typically compost or topsoil inputs. So we would expect to see higher carbon in those areas. If we look at depth trends, so this is just showing averages on each of these categories by depth. You may not be able to read that top legend, but pink is raised beds, blue is in-ground food producing areas, and then green is non-food producing, red is natural vegetation, and yellow is turf grass or lawn. So basically what you can see is if we look with depth, that higher carbon is fairly significant in the top 40 centimeters about in those food producing areas. And then at that point, there's not as much difference between those food producing areas and non-food producing areas. So it's top 40 centimeters where we see that higher carbon. If we look at carbon stocks, we did get bulk density estimates because we had sample mass from the cores. So carbon stocks were highly variable. This is something that's been shown in other studies, 4 to 80 kilograms of carbon per meter squared. But on average, they were pretty high, 26 kilograms of carbon per meter squared on average. So that's as high as what we would expect to see under some of our prairie, natural prairie vegetation, certainly, and in some cases even higher than what we would expect to see in this part of the world. And those carbon stocks were also much higher, significantly higher in food producing plots. So any raised beds or in-ground food producing areas had significantly higher carbon stocks than non-food producing gardens and turf grass, and were not were equivalent to natural vegetation. So the carbon stocks are not necessarily significantly higher than natural vegetation, but definitely than turf grass and non-food producing areas. And these sort of patterns are similar to what's been shown in other studies. Rich Puyat, I think John Galbraith was on a couple of those papers, multi-city study in the US, study out of China, and then Bryant Scherenbrock's work in Greater Chicago. So similar to what we've seen in terms of the variability of carbon stocks and their elevated status in urban areas. Similarly with carbon, soil phosphorus has also been shown to be elevated in urban areas generally, can be very variable, but there's a number of studies that have shown increased total phosphorus associated with urbanization. And this is a study out of London that's just showing anything in red in that top right there is higher phosphorus, blue is lower phosphorus, and the London city center is right in the center. So on average, phosphorus is higher in the more urbanized areas of London. And again, this has been shown in other studies. This is not surprising either. Solid waste, organic and pet waste, building materials, fertilizers are dramatically concentrated in phosphorus relative to natural systems. So more intense human activity generally leads to higher phosphorus levels. And if we look at what we would see in terms of phosphorus patterns in urban versus non-urban areas of Minnesota, this is a data set from our soil testing lab here at the University of Minnesota. So this is more than 130,000 samples from a lot of years. But in the pink on that histogram is all the samples from outstate Minnesota. So not from Minneapolis, St. Paul, but from non-urban areas. And the median available phosphorus, Bray phosphorus, is 27 parts per million there. The samples from Minneapolis, St. Paul are significantly higher, 43 parts per million. And similarly, if we look at our data set, at least in our top depth increment, it's even higher, probably because we included these food producing areas. So 65 parts per million Bray P, which is very high. It would be very high for any soil test. So not surprisingly, we are seeing quite high phosphorus. And that topsoil phosphorus, again, is significantly higher in food producing areas. So raised beds or in-ground are going to have significantly higher phosphorus levels than turfgrass lawn or natural vegetation. Similar to carbon, we see depth trends in phosphorus that extend below the surface. So if we sort of just look at average phosphorus available P across these depth increments, what we see is that our food producing areas, in-ground and raised bed food producing areas are significantly higher in available phosphorus, almost all the way down to 100 centimeters, so to a depth of a meter. So there's clearly some phosphorus leaching happening there as well. And then non-food producing gardens are also higher than turfgrass lawn or natural vegetation. Again, not surprising, people have probably put phosphorus containing fertilizers and compost on their non-food producing gardens as well. And phosphate containing fertilizers have been banned in Minneapolis, St. Paul for turf grass for quite a while. So there's not really an elevated signal of phosphorus in the turf grass or lawn treatments. pH, so it's also common, again, many studies have shown this, that the elevated pH in urban soils is very common. Particularly in our area, we tend to have calcareous subsoils, and so any sort of cut and fill activities or removing of topsoil over the course of development is going to expose much higher pH materials. We're also a northern climate, so quite a bit of road salt is applied, sodium and calcium-rich salt products, so those non-acidic base cations can get the pH up to near neutral, where that's sort of applied. And then high artifact or debris content in urban soils also can elevate pH. So if we look at the natural topsoil pH that we might expect to see here in the Twin Cities area, it's probably between 5.5 and 6.5. These are just estimates from Ramcharan et al., the 100-meter soil grids maps. And so, 5.5 to 6.5 is probably about right for eastern Minnesota. What we see, though, in our urban areas is significantly higher than that. So if we look at outstate Minnesota, the median, again, this is from our soil testing lab data set, the median pH is 6.7. If we look at our urban samples, Minneapolis, St. Paul, it's 7.3. And similarly, the samples that we've collected in this data set that I'm showing you now over the last 5 years, our median soil pH is 7.1. So definitely some elevated evidence of elevated pH. There's no significant difference between land use categories with pH, but the pH values under urban food producing areas are much less variable than under natural vegetation or turf grass and lawn. Probably not surprising because people are applying generally the similar types of amendments in food producing areas, and so the pH range is just smaller, but definitely elevated relative to what we would find naturally. So some conclusions and maybe some implications of the beginnings of this data analysis for ecosystem services here. As I said, there's an interest in Minneapolis, St. Paul in evaluating urban food production as a viable green infrastructure strategy. And so the question is, how do soil properties under urban food production compare to other land cover or land use categories? And so I think clearly these preliminary results show that there's increased carbon, phosphorus, and sometimes saturated hydraulic conductivity, especially in the case of raised beds under urban food production. The effects on carbon and phosphorus are by far the most pronounced, and phosphorus is the deepest. The effects are the deepest in the soil. And urban food production does not decrease KSAT, at least, relative to green spaces or turf grass. So encouraging urban food production wouldn't necessarily lead to a decrease in KSAT in the topsoil, at least. And urban food production results in similar but less variable topsoil pH than turf grass and green spaces. So I think the big take-home message is that urban food production doesn't necessarily have negative impacts on important soil properties, at least the ones we looked at here, can provide a host of other services that have been shown in some other work. And also that the increased carbon, phosphorus, and pH all favor contaminant immobilization, especially with respect to lead. So this is a really important issue in the Twin Cities, and that might lead to decreased lead bioaccessibility. So urban food production may in some ways be remediating unintentionally soils that have low to moderate levels of lead contamination. And so that is an important service that people may be, again, unintentionally providing as they go about doing urban food production. So I'll stop there. I had a few other comments, but I don't know if I'll be able to hear any questions, and I may be up on time. A lot of people participated in this work, many students. Again, most of this was opportunistic, so they jumped in over the course of the summer, and some community partners, stakeholders, and grants that this work was a small part of. So thank you very much for your time. I appreciate it.
Thank you, Nick. Thanks very much. So our next speaker, we're going to go moving from the arid from the urban landscape up to the till plain and other landscapes of Canada. And David Lobb is our next speaker. And here we have him. So David's going to be talking about the changing demands on soil survey and the future, or what the future may hold.
What the future may hold for you. What it has happened to us. Okay, I'd like to thank David Hopkins and the organizers for inviting me to speak to you today. And as noted in the presentation summary, which I believe you all have, I'm here to highlight what I see as the major needs in soil survey based on my experience as a modeler and as a policy informer. For my presentation, I will start with a bit of background and then cover some areas that I think need or bear some discussion amongst yourselves, and then I'll work towards a view for the future. Now, I presume most of you have no idea who I am, other than that brief little introduction that Dave gave. So it's probably a good idea if I give you a bit of my background so you know where I'm coming from on this. I grew up on a cash crop farm in central Canada, near Clinton, Ontario, and I studied earth and environmental sciences at the University of Toronto for my bachelor's degree, and then soil science for my master's and my PhD. While carrying out these studies, I worked across central and eastern Canada before moving to western Canada in 1999, so I've been out here for 25 years, where I'm a professor in landscape ecology at the University of Manitoba. Now, over the past 35 years, my research program is focused on soil erosion and sedimentation, and those are all sites where I've worked and collected samples and analyzed across the continent, specifically on enhancing our understanding and management of these processes, the development of measurement techniques, and the development of models, which is part of the reason why I'm here. My research has largely been carried out in agricultural environments, extending from the point scale to the landform scale, to the landscape scale, and beyond to watershed scales, all the way to continental watersheds. My research has been the basis of assessments used in soil conservation, planning by farmers, and extension services across Canada, and in the development of assessment of soil conservation policy and programming by provincial and federal government agencies, and in their contributions to the international and global initiatives, such as the OECD's Agri-Environmental Indicators and the United Nations Global Soil Partnership Programs, Mapping and Modeling, and the Black Soil Mapping was referred to this morning. The interests in this research are not limited to the degradation of soil and threats to food security, but they certainly are focused on that. They extend to the degradation of water resources, specifically runoff, the fate of runoff, nutrients, and pesticides with that runoff, and they extend to the mitigation of and adaptation to climate change, specifically things such as carbon sequestration, greenhouse gas mitigation, and the impacts of weather extremes. Now, what underpins all of that work is soil survey data for the contextualization of field research and the application of the models that I use. Through this work, I've developed a great appreciation for soil survey data and an understanding of its strengths and its weaknesses or limitations and its future needs. And a quick disclaimer before I get too much further into this. This perspective is based largely on my Canadian experience, but I believe it's relevant to the discussions you're having here about the future of soil survey in the United States. So the first point, and I can't read that at the back at all, so I'll have to read it here. Soil and landform classification is the first one of the 5 things I'm going to cover. There's increasing pressure for international and global modeling and mapping related to soils, which demands a universal approach to characterization and classification. But the classification and taxonomy is well developed in most countries, but there are multiple systems. And there's substantive differences between these systems. And just for an example, let's mention the US soil taxonomy and the Canadian system soil classification. There's a border between the 2 countries, and you wouldn't think that there would be much of a difference in the soil survey systems, but there are some substantial differences. And as an educator, having to teach soils and pedology, it's really hard to explain to the students why there is systemic differences between the 2 systems. And I say, well, there's multiple systems, it's not just 2. And so when you deal with global issues, it becomes pretty complicated. Anyway, I can live with the students complaining about that. What I have a major difficulty with is the lack of a unified, coherent landform characterization and classification system. And being a geomorphologist, I found this really surprising when I started to dig into this 20 years ago. There are a variety of terms that are often used by geologists, geomorphologists, and pedologists to describe the shape of the land surface. And there are agreed upon descriptions of form, like convex, concave, convergent, and divergent. But the classification of form capturing scale and degree is weak. There are terms to attempt to capture these concepts of form and function, but these can be very context-specific and open to interpretation, often leading to unnecessary confusion when I talk to my colleagues in other parts of the country, let alone other parts of the world. Some good examples that I'm going to go through that I'm familiar with, and there was one that came up earlier today, I think actually in Nick's presentation, hummocky. Hummocky means a lot of different things to a lot of different people. Holy smokes, it's a problem. Undulating versus rolling, there's different examples up here. These definitions, everyone has their own definition of what rolling and undulating is. Crest versus summit. When I talked to Tom Schumacher at SDSU, we got in these huge debates about whether something was a crest or a summit, and there's no consistency in how we approach these things. But probably the most difficult one is slope gradients with unspecified slope lengths. This is something that is in the soil surveys and is a real difficulty dealing with. Apart from the inconsistencies illustrated here, slope gradients and slope lengths found in the soil survey data sets refer to different measures. And you've probably all run into that at some point. It may not be such a problem in the States, but in Canada it is. Every surveyor had a different approach. Sometimes dominant slopes, these are quotes, sometimes dominant slopes, sometimes average slopes, sometimes eroding slope lengths, for people like me interested in erosion, and sometimes the total length. All different, and it was rarely written down, but when you dig into it, they all had different approaches. Using existing landform data in the soil survey databases often requires quantitative gymnastics to apply it to models of soil and water movement within the landscapes. And this can get rather complicated here, as I'm going to show you in a minute. So when we tried, this is an illustration of something that I worked on, trying to come up with a data set for slope length and slope gradient that was actually accurate for across the country in Canada to run erosion models nationally. And to do that, we had to do a lot of these quantitative gymnastics, coming up with a defendable approach to actually quantifying what would be the most appropriate length and gradient when you run erosion models on the soils database, translating from what may have been in the database to what actually is out there. Historically, landform data has been part of the soil survey databases With current capability to quantify and analyze topographic data, much more can be done to characterize landforms and the topographic features of these landforms. Specifically, the micro, meso, and macro topographic surfaces, capturing slope curvatures as well as gradients and lengths. We have the capacity to do a lot more in the terms of landforms, and we probably should. I would argue that when it comes to modeling the movement of water and soil within a landscape and the materials within that water and soil being moved, that landform data is equally as important as soils data when it comes to modeling. I didn't see anyone yell at me about that, but it's true. That drives, when we do sensitivity analysis, it's the topography that drives much of what goes on in the landscape, more so than soil. Now, given this perspective, I see a great need for leadership in landform characterization and classification. And there's no better group than the soil survey community to do this. And I would challenge the soil survey community here, as I do in Canada, and I probably won't get any uptake here either, as I haven't in Canada, but that's the community that should be coming up with a sensible system for landform data that goes into these databases that the data jockeys use when they run these maps of what goes on nationally and globally. Okay, that was a little bit of a commentary that wasn't in my notes. Okay, the second point I wanted to deal with is the soil resources data. As noted above in my comments, soil survey data is critical for modeling land-based agriculture and environmental processes. But the data is often not adequate for the task given the current demands. In particular, spatial coverage can be problematic. Although we have complete maps at coarse scales, there are significant gaps. Sometimes very large areas are missing soils information. So when I show this to the politicians in Canada, they think, oh, you've got the whole country surveyed. And I try to point out there's very, very large areas where there is no data. This is just somebody's conceptualization of what's probably there. We don't actually have data. Anyway, and often the fringe areas of agricultural landscapes are missing, such as riparian areas, field edges, etc. Consequently, the coverage is often not at a fine enough scale to provide acceptable coverage for modeling processes as they operate within the full agricultural landscape. We're not just modeling what goes on within a field, we're modeling what goes on within a landscape or watershed. These conditions limit the accuracy, precision of assessments, and create large uncertainties in the output from those models. There is a way forward in dealing with these limitations. Major advances in pedologic modeling have been made to fill in needed data. And I suspect many of you have been working with those or come in contact with that type of data. These pedologic models are often topographically based, at least the ones we use in Canada are. They're driven by topography. And on this section of land, it's a hummocky prairie pothole landscape. The optimum scale for topographic data collection is about 5 to 7 meters to capture the landform that's driving water and soil movement. So pretty fine. But this is not adequate to capture the fringe areas of this landscape, which is a tillage step. So if you didn't know, that's a section of land that's 1 mile by 1 mile, prairie section. And this is a wetland from that, and there's a tillage step that goes around that. And that's where the majority of the soil that's eroded from the landscape is moved to. It's on that tillage step. But you can't capture that unless you're down to a scale of 1 to 2 meters. Research must continue in the development of remote sensing and techniques such as radar, like LIDAR, or infrared spectroscopy. That's absolutely critical. And there's a need to encourage and expand such technology or technology innovation to enhance soil databases. But there's an equal need to maintain active field soil survey programs to support this innovation. And I suspect I would get 100% support from the people in this room on that. Not only do we need to tackle spatial variability, we need to better understand and reflect temporal variability within soils databases. I'm acutely aware of this issue through my research on soil erosion. Soil loss and accumulation can be substantial over relatively short periods of time. Recognition of the process of tillage erosion as a separate erosion process from wind and water erosion, and the process that has the greatest impact on soils as we see them in farm landscapes, has heightened our awareness of the spatial and temporal variability of soils, and the need to capture this variability in models of soil erosion, soil carbon dynamics, soil productivity, et cetera, et cetera. These temporal challenges can be greater than the spatial challenges. Filling in gaps is easier than recreating the past when it comes to soils. Soils databases do not capture these changes. They are often frozen in time, the year that the soil was sampled. And using this old data does not allow for accurate prediction of agricultural and environmental processes as they're operating today. Soil survey is an ongoing need. There needs to be a soil survey to be able to keep databases current. And another one about land management data. This is a bit off the soil survey side of things, but I think it's important. In modeling agricultural and environmental processes, soil and landform data, along with weather and climate data, are only part of the required data. The other data that's required is soil and crop management data, the land management input data to these models. For a snapshot assessment, simply knowing what soil and crop management practices are being used at the time may be enough information to model the current process behavior, but it's insufficient for assessing processes such as soil erosion, carbon sequestration, et cetera, which require long-term, decades-long assessments, understanding soil and crop management practices and their impact on soil properties. In assessments of soil erosion, its cumulative effects over time, we must seriously examine the driving forces of soil and crop management practices. We must recognize that the nature of these practices differs considerably across regions, but it may also change considerably over time, even with a short time of a few decades. So with respect to soil management, we have conservation tillage, conventional tillage, no-till, which will all come up today. What constitutes these practices and systems has changed considerably over the past few decades. No-till today rarely looks like no-till 40, 50 years ago. Furthermore, with the recognition of tillage erosion as the predominant erosion process, has come recognition of the need to consider soil movement in addition to crop residue incorporation in modeling of soil erosion. Particularly for practices such as high disturbance seeding, which is shown here, and vertical tillage, which is also shown here. These practices may be part of a conservation tillage system, but they move a lot of soil and they cause a lot of erosion and cause a lot of degradation. With respect to crop management, in the past 50 years, absolute crop yields, field averages have increased by a factor of about 3, showing this data from Canada. So this is showing winter wheat for Canada over the period from 1961 to 2016, a 3-fold increase in crop yields. Consequently, the crop residue and carbon inputs have increased considerably and cannot be ignored, although they tend to be ignored in all the carbon modeling. So it's a real problem that these things are considered to be fixed in time. Crop and soil management practices have changed. For modelers, such changes are very problematic. The default is to assume that these practices are constant over time and space. It's much simpler, but certainly not accurate and creates great uncertainties in the models that we run. The solution to the problem seems pretty simple. Bring together the agencies responsible for the land management data, coordinate, sustain, and comprehensive data collection activities, which generally isn't done, and couple these with data collection activities with land resource data collection, soil survey, coupling those two. They have to be done in concert. And have a single custodian for both land resources and land management data. Part of the problem is, even if you can get access to both sets of data, they're not managed by the same agencies in the same fashion, and it's very difficult to work with. There is one agency that's best suited to meet that challenge, and that is the National Soil Survey. So to get on to the final point, what the future holds, I'm certain that there will be continued interest in soil and landform data for the purposes of environmental modeling. It's certainly going to be there. There's no question about it. And there will be an increased demand for greater accuracy and precision to improve the model performance and reduce the uncertainties associated with those outputs. And this demands a robust national soil survey with a broader scope of responsibility. And I'm just going to end on the state of soil survey in Canada, which some of you may know. I talked to Dave about this a little bit earlier. The federal government does not have a pedologist. We no longer have a soil surveyor. We have people that may have soil surveyed in the past, but there's no active soil survey program. Within the 10 provinces, I think that there are 4 soil surveyors. and they're not very active as far as I can tell. Some of them are doing more than others, but it's not a coherent program. And what Soil Survey now, and soils databases now, is GIS management. And people are running data with no insight into what all those issues that I raised. And they're producing maps, produce lots of maps. And I would caution you, and I would encourage the USDA to make sure you maintain a vital, robust soil survey, because if you don't, you are going to have serious problems implementing any of your programs with any credibility with industry or the public. That's my final comment, Dave.
Thank you very much, David. There's just like 1 minute for questions or comments if we have some in the audience.
Okay, there must be somebody who disagrees with some of that. Dave, you must have some comments if no one else does.
You know, it's interesting to watch decadal changes in governmental programs and how, you know, I've been going up to Manitoba for a long time with the, you know, the winter meetings of the Manitoba Soil Science Society, and the graduate students in the 80s, in the mid 80s, were talking about what was going on in Canada, and you know, we were very impressed with the, you know, the Kansas program, database work, and things along those lines. And so they have, and is Clarence still active to some degree? The Canadian Land Resource Network was active. I was introduced to that in the very early 2000s.
It came and went.
It came and went. So,
yeah,
we have to fight for things, I think, is part of the idea.
It's a real challenge in Canada, and you see this in other countries. And United States has also suffered losses and will probably continue to, as politicians see complete maps, as that example I showed, see a complete map. Why on earth do you need a soil survey?
Thanks very much.
Okay.
Folks, our next speaker is Dr. Kevin Sedovic. He's the superintendent of the Streeter Research Station, which is our range management station down in it's 100 miles to the east of us here, a little bit south. Kevin and I have known each other for a long time, so it's just great to have a range scientist to share some ideas of the prairie with us today. So thank you very much. Sorry, I'm gapping here. So he'll be talking about native ecological site work and such and such.
Thanks, Dave. Dave, can I borrow your mic? I'm not a big person to stand behind a podium, if that's okay.
Good luck on that.
Thank you. You hear me fine? All right. Well, it is a pleasure to be here today. I came in this morning a little early, and I'm one of them extension specialists that works on the talks at the last minute. So I was working on this late last night where they never got my PowerPoint till this morning. So I do appreciate the opportunity to come here today. And my topic, if you look at my title, it's Species Composition, Trends, and Impacts on Native Ecological Sites. And you say, what does that mean? Species composition on these trends. And so my perception on this is, where are we at in terms of current species composition and this change in trends and how it affects our native plant community or these ecosystem functions. And so when you look at today's communities in terms of our grasslands, it really is that invasive plant species have really taken over the world. For those of you who are a little bit into plants and you get to travel throughout the country, you'll notice that invasive species have dominated or become dominated across our ecosystems, no matter where you're at in the world. When I was a younger scientist, I went to Hawaii in the 1990s. If you've ever been to Hawaii, Hawaii was dominated by exotic species. And I'm like, man, I hope the inland side of it never gets that way. And it really has today. The shift we've seen in the last 30 years, it's invasive species do dominate. When I sat there in my talk, I wanted to put a video of Godzilla walking in on there and eating up all of our rangelands on this shift across there. But I couldn't find a really good one, so I decided to punt. So if you look at the current climate conditions and management strategies, we've seen this reduction in plant diversity. And the plant diversity is a major driver in terms of soil function. We replaced many of our plant species, which you see today is you're dominated by 1 or 2 plant species. And so the diversity now changes what's going on in that ecosystem function. In the Northern Plains, our big issue has been bluegrass and smooth bromgrass invasion, probably over the last 50 years. And there's some example of bromgrass to the top and bluegrass at the bottom. If you look at probably the most dominant or most consistently talked about annual invasive is bromgrasses in the western U.S. It's still today the #1 economic loss to the ag community and environmental community. That's been that way for probably the last 50 years. And so annual bromes still are a major issue, and they've been a major issue for over 100 years. In the south, you have eastern red cedar. We've seen a lot about woody encroachment. That's one of them issues that I think has been an issue for a long time. But it's one of them issues that we really could have taken care of earlier if we knew how to manage like we see today. So when we look at these invasive species, annual bromes have been a problem since the 1920s. It was probably the first invasive species that the government really looked upon early and tried to be aggressive at controlling annual bromes. How did we do? Not very good, did we? Annual bromes today are still the #1 issue like they were in the 20s. And annual bromes are just a devil. They're very difficult to deal with. The eastern red cedar became an issue in the 50s. The government put more dollars in eastern red cedar. The problem was we know how to control eastern red cedar. Light a match, burn it off. What did we see in the 50s and 60s and 70s that kept us from burning? Smokey the Bear. Absolutely. We did not want to burn. We were taught that fire was bad. And that was what happened, and we see eastern red cedar today as a major issue. For us, our big grass invasion was really smooth bromegrass. It came in the 60s and 70s. Why did bromegrass increase? Because we took away management. The big push in those days was tall nesting cover for waterfowl. So let's take cows off the landscape, and let's get tall cover. And what do we get? Smooth brome. If we would have known better in the time, we'd have known we should have grazed that bromegrass or that plant community, we would have had less bromegrass. Today, our big issue is Kentucky bluegrass. It really started encroaching in the mid-1990s. And yes, this is your lawn grass that you probably have in your yard. And it became aggressive probably in the mid to late 90s. This grass is probably one of the fewest of the group that is driven by climate change. Climate change was a driver in terms of longer growing season, more moisture. No matter what we did, we didn't manage it properly, bluegrass became an issue. And we still struggle with those today. So when you look at invasive species, they were really driven in terms of management side on the agronomic side. It was the dollars that were driven in terms of livestock industry, forage production, and even today we still have a $20 billion annual loss in forage production due to invasive species. Just think about $20 billion today. And if you look at that, the other side of that is the inputs we put into controlling invasive species. This is actually a picture of in Idaho where they're spraying cheatgrass with a very big plane. I was just kind of shocked when I brought this up. But so the benefits of this loss in forage production is the herbicide industry. We put dollars into herbicides to try and control. And how good is that going? Not very well. In the last year, the federal government always looks at programs, looks at needs, and the development for invasive species, the government puts programs in place and dollars in place. We put in hundreds of millions of dollars in terms of government funding to go toward invasive species. We spend roughly $50 million a year just on woody encroachment. So you can see the costs and agronomics behind it. The push over the last probably, I want to say 2 decades, but more importantly the last decade, we see this shift in looking at invasive species ecological value versus strictly an agronomical value. And we try to look at, we see that as we get more invasive species, we lose ecosystem function. And we lose ecosystem services from these invasive species. So there's been more and more research being done to increase this biodiversity question. And so most of you have heard the buzzwords on this, and this is really looking at trying to create a different disturbance ecology to reduce the invasive species. And as a scientist, I struggle with this because we are so far gone. And we want to try and come in and fix it today. And it's just a very big task to do. And the buzzword we typically see today, and you all know it, is regenerative ag. Let's do regenerative agriculture as a tool we can do to fix things. And the concept is great, don't get me wrong. Most of regenerative ag was pushed, it was almost on crop ground, but we see it more and more coming on our rangeland systems. And they really revolve around disturbance. And so when we look at grazing and fire, we already talked about fire was viewed as a bad tool in the 50s, 60s, and 70s. And now over the last 20 years, it's viewed a little more positively. Now, if you live in North Dakota, ranchers still view fire as not good because the risk, in their opinion, still is not good enough to do it. Grazing has historically been looked at negatively, and it was always looked at on the overgrazing question. Once you bring in proper management, grazing is a phenomenal tool to deal with invasive species. And it's actually gotten to the point where we see, I've always got a kick out of watching some of these social media stuff on what cows do. Cows fart or they burp and you release methane. But that shift has almost been now cows are good, which I like. I like to eat beef. I think cows are a good tool. But the perception today is these are actually being looked at almost opposite as good. But they still have to be done properly to get a response on what you want to do for invasive species. And we still struggle. Even with those tools today, disturbance ecology is slow. So what does this have to do with soils? Now, most of you are probably soil scientists or soil conservationists, and I'm a range ecologist. And as I went through college, I was always told that rangelands made soils. And the soil scientists looked at me like, you're a dumbass. Because we all know soils make the plant community. And I eventually grew up and figured that out. But when it comes to invasive species, they can shift that and actually change the soils the other way. So you have this picture here. This is brome grass invasion. You have a healthy grass stand. It's not a very good picture. But when we see the northern plains is when you get too much of these grasses, we create a lot of litter because we produce a lot of biomass. That litter eventually breaks down into a thatch layer, which sits above the mineral soil. That thatch layer impacts function of that soil and biology. Microbiology for one, hydrology for another. So that function now becomes an issue and can drive soil change. It's a long change, but that can impact the soil. So this is a picture of a brome grass area. You see the brome grass, bluegrass, I'm sorry, at the top. You see that litter layer? I think my pointer works. Does the pointer work here? Oh, there it kind of works. Here's your litter layer. This is your thatch layer, and this is mineral soil. So you can imagine when we get rainfall, what happens if you don't get a lot of rainfall. When you get a lot of rainfall, it actually runs off. You can look at what happens to the microbial populations. This can actually change the soil. So I might actually be right when it comes to the invasive species on soil function. So our goal, I tend to talk long. So our goal is trying to create greater biodiversity across the landscapes. This is just a nice picture of the grassland station, trying to create more plant species. With more plant species, you create a different architect of rooting structures, rooting depths, rooting styles. Some are lateral, some are tap-rooted. That growth in root structure creates different porosities in the soil profile. You also create more carbon in the system. One of the greatest carbon capturing environments we have are rangelands today. I know foresters think they're the best. In my opinion, it's rangeland captures even more, especially in the US. And so this is our goal, and it's funny, you look at these pictures, this is what they give turf grass for credit for root development. Not very good, is it? And it actually isn't very good, but it's still better than that picture. So our goal is to increase plant diversity, which can increase pollinator habitat. It can increase soil microbial diversity and richness across that landscape. So I'm going to show you, I got a little bit of time to show you a little bit of data. So what happens when invasive cool season grasses invade different ecological sites in the northern plains? This is one down from the Fort Pierre National Grasslands where we looked at a clay ecological site in MLRA 63. And so if you look at the graph here, this is native range, which is the blue bar. This is Kentucky bluegrass dominate, the red bar, and this is smooth brome grass. This is 0%, 50%, 100%. So you can see as brome grass invades, herbage production goes up. Where's the cattle market been in the last decade? Animal numbers are going up or down? They're going down. Cattle numbers are going down. We are actually producing more grass in the northern plains today than we've ever produced. Our production is much higher than it used to be. So if you look at Kentucky bluegrass, as Kentucky bluegrass goes up, production actually goes down. And native range tends to be stable. And so if you look at this in terms of the NRCS tech guide, and the RFV for a clay ecological site in South Dakota in 63A, this is what the current tech guide talks about for clay production at 2,500 pounds an acre. And we're producing over 4,000 pounds an acre. So if you think about more biomass, that's more litter. So now we're going to deal with more litter, which is our confounding impact on our soil health. And so the dotted dash there is actually what they call the high end for relative forage value for a clay ecological site. And we're well above that. The struggle in this region is producers want to increase cow numbers on public land. And the agencies do not want to do that because they think it's going to produce better habitat and better rangelands. The reality is the agency is wrong, the producers are right, but how do you get that, and how do you get that to occur over time to where they're both happy in the end? If you look at, I'm going to show you, this is some data that looks at what happens to the plant community. So if you just look at the yellow bar, smooth brome has a positive effect on production, negative on diversity, negative on richness, negative on bluegrass, negative on native range, negative on forbs. It's not a good plant. And brome grass can dominate a plant community if you don't graze it or manage it properly. Native range in the bottom is basically neutral or positive, and you can see bluegrass is actually negative, but at the level it's at in the grasslands, it actually sits at being neutral in some of these different characteristics. So I'm going to end with some of these slides from western North Dakota. This is MLRA 54. These are regression lines for species diversity. So the first one here is actually crested wheatgrass, and as crested wheatgrass increases, the plant diversity declines. With brome grass, you see the same thing. Bluegrass actually in the more arid country or arid regions does not affect plant diversity. It just doesn't like those drier sites. If you look at which ecological sites are more likely to be invaded by cool season grasses, these 6 are the ones that will more likely be invaded. It's a clay pan site, a loamy site, clayey site, the sandies, limey residuals, and thin clay pans. Those that are least likely to be invaded, so these are the ones that you want to almost focus on keeping them healthy, are very shallows, and thin loamies. What that tells you is brome and bluegrass need moisture. The drier sites, they just don't do very well. And so on the grasslands, they try to make sure they keep these as healthy as they can. So if you look at management goals, so what is our goal? Our goal is to change that architect in the soil profile to get more roots, more different roots to change that. And in reality, what we're trying to do at the research station is reduce this litter layer and reduce that thatch layer so we can change the function. If we can change the function, hopefully we can get more native. And this is just an example. When we've done this over a trial now, with removing that thatch layer, we can increase, this green bar is species richness, this is diversity. You can see we've increased richness and diversity versus no removal of thatch after 2 years. So we do see a positive response. The trick is how to remove the thatch layer. Here we're doing it physically. We're going out there and actually removing it with a machine. But how do we do that with management? And that's still where we're at today. So in conclusion, invasive plant species are still taking over the world. And it's our goal as scientists and as managers or conservationists is to find ways to turn this around, to increase biodiversity. And to do this, you have to disturb the land, the resource. You can't just leave it idle or not manage it very, very aggressively. And what I mean is you can't lightly graze these ecosystems, especially in the Great Plains. It's different in Arizona, it's different in Nevada. They're drier climates. But in our country, you need to manage these systems. This is a picture to your left on a patch burn grazing. So we've burned it and we graze it right after we burn it. And you can see that's a pretty good disturbance. The year later, this doesn't show up very well here, but that's big blue stem. Our diversity responds to that with recovery. So you do the disturbance, you still have to have sufficient recovery for those plants to respond. This is what's been happening over the last probably 20 years, is we tend to graze too light. We're afraid to graze our grasses, and we get this buildup of litter. So proper management includes periods of heavy disturbance by livestock and or fire, and then you get rest. And we do see an increase in biodiversity by doing that. And so in the end, don't be afraid to graze your grasses. I tell this to producers, I tell this to land managers, don't be afraid to graze that resource. It's evolved through grazing. Don't baby it. In our region, you can graze them effectively. So I got 1 minute left. Any questions? Yes.
I'm a little curious about how the plant diversity is linked to animal diversity, and I didn't see any slides about that, but I'm curious, I'm assuming those two things are linked, and there's generally a decline in animal diversity, and I assume that's linked to plant diversity, and if you can say anything about that, I'd be curious to know.
Yeah, that's a great question. You probably heard the question, and it is, as plant diversity goes up, pollinator species go up, wildlife goes up, so we do see above ground, we do see a benefit of the users of that resource. We also see more resiliency within the plant community in terms of livestock production. So we can get rid of the highs and lows, which we see now, and we can create better resiliency in on our grazing performance, as well as wildlife use, as well as microbial population. There's some cool data coming out now that as we graze that resource properly, we increase microbial population in terms of diversity and richness. You bet.
Thank you. Folks, our next speaker is Dr. David Toledo, who comes from us from just right across the river at the ARS station. And so he's going to be speaking right before lunch on rangeland resilience, which we've just been introduced to a bit, okay? And adaptations to climate change. Thank you, David.
Thank you. Good morning, everyone. I am a rangeland scientist, not a soil scientist. I study the grass, that green stuff above what you study. And I'm going to follow up a little bit on some of the things that Kevin was talking about and hopefully provide a segue to one of the tour stops that you're going to be going to tomorrow. So a lot of the research that I'm presenting here comes from those sites that you're going to, or one of the sites at the Northern Great Plains Research Lab that you're going to be visiting tomorrow. So my talk's title is Building Rangeland Resilience to Adapt to Climate Change. First of all, I couldn't have done all this work without all the collaborators that are part of these different projects, the support staff at the Northern Great Plains Research Lab and the other scientists, Nature Conservancy, who helps us with burn training and helps us during burning days, several different ARS, particularly Sydney location, and NRCS here in North Dakota, and the many landowners who have contributed as part of a customer focus group that we have and have provided really great feedback, both positive and sometimes negative, which has helped us build up our research program. So this is data from the Central Grasslands Research and Extension Center, where Kevin is a leader right now. And the data show that increase in Kentucky bluegrass sometime in the late 80s to mid 90s, which coincides with a period of pretty wet period. So kind of climate change, that wet period contributed to that increase in bluegrass. And that's continued to increase. This is National Resource Inventory data that show that over 50% of the acres sampled in North Dakota, South Dakota, have bluegrass in them, and that has continued to increase. So we have bluegrass throughout the Dakotas. It's expanding its range, and it has become more of a problem. Kentucky bluegrass is a cool season grass. It grows during the cooler, wetter part of the year. So as that bluegrass increases, and we have more and more of it, and less of those warm season species and forbs, we're actually reducing the length of the grazing season too. So that's one of the implications, management implications of this work. So behind me, you'll see a state and transition model area for MLRA 54. And this is the Loamy Ecological Site. We're supposed to be dominated by western wheatgrass, green needlegrass, other C3, other cool season grasses. But with invasion of bluegrass, it starts heading out of that native state and goes into this invaded state, which there's no arrow back from, if you can see in that state and transition model. So once we're invaded, we stay invaded. And we can do management practices to try to reduce that bluegrass, but we're not getting rid of it. Good thing, as opposed to that brome grass that Kevin was talking about earlier, bluegrass, it has some sort of nutritive value. So of all the invasive we could have had, it does provide a good ecosystem service in terms of forage quality and quantity, because it is very productive. However, when it gets hot and dry, if all you have is bluegrass, then you start running into problems as a producer, because you don't have anything else to feed your animals, or wildlife pollinators start running into issues because there's nothing else growing out there. So as we move out of that native state, we move into this Kentucky bluegrass state, which is also a very resilient state. Kentucky bluegrass is a very resilient grass. We've tried to herd it many different ways, and it always seems to come back. It has a way of always making it back. Very, very resilient grass. So in areas where we see no Kentucky bluegrass invasion, we tend to see nearly continuous grass cover. There's still some bare ground, but we do see the bare ground, areas without litter, so not that thatch layer, thick thatch layer and litter layer. Pretty high soil aggregate stability, well-developed brown A horizon, no compaction layer, and there's that diversity of functional and structural groups that provide that different rooting structure that Kevin also showed in one of his slides. Again, as we start moving out of that western wheatgrass, green needlegrass dominated state, we move into that resilient bluegrass state, and what we start seeing is continuous cover of that bluegrass. That picture illustrates it very well. We talk about these bluegrass slicks because it just starts falling over if it doesn't get utilized. Creates that really thick thatch litter layer. You lose diversity of plant species, lose forage diversity. You start seeing the effects on A horizon and infiltration. That litter layer is very hydrophobic when it's slightly wetted. So during a short, not very intense rainstorm, most of that is just going to run off. Eventually it does start kind of permeating and actually starts accepting some water. But then you have that root layer of root mat of Kentucky bluegrass where a lot of that water is going to kind of reside, and it creates this reinforcing feedback where it's just benefiting itself and is not providing that deep water that some of our native species need, or deeper water. When you combine all this with some of our climate projections, we see that we're expecting drier, hotter climate moving forward the next few decades. As I mentioned earlier, Kentucky bluegrass is a cool season species. We're losing a lot of our warm season species. So when we start thinking about this, and if all we have is bluegrass, we start running into an issue of what are we going to be left with? And what can we do to kind of be proactive about changing some of this and bringing back some of those natives and some of those warm season species? We've done some forage analysis on bluegrass growth curves throughout the year and looked at forage quality of that bluegrass. And even in a good year, so these are data for a fairly wet year, it does not really meet the nutritional requirements of a cow-calf. So when it gets drier, we have data for drier years too, it's even worse. So we definitely don't meet those nutritional requirements. So we need to try to improve that diversity of our plant community to actually provide the services that we're supposed to be providing and in a way maintain that soil health. So the good part of this is that we've crossed a biotic threshold at this point. We have not yet crossed a physical threshold. We still have that. We still have an A horizon. We still have that soil surface layer there to provide the services, and we can kind of start shifting this through using some of the management practices that both the state and transition model, Kevin, some of our research have shown work, which are prescribed fire, prescribed grazing. So we started an experiment. So I started an experiment several years ago where I was doing prescribed fire. I started talking to landowners here in North Dakota about the great things that we're learning about prescribed fire, but one of the things that I kept getting back was like, why are you burning when you can just graze? It's the same thing. And I did not think it was based on research, based on theory, but we did not know. We did not have the data for North Dakota to prove that these things were different and to see the effects of that burning and grazing in our grasslands. So we started an experiment to look at season-long grazing, which is a predominant practice in this area, mob grazing, multi-species grazing, prescribed fire, and then a prescribed fire treatment where we then graze it. So we burn in fall, then we graze it in the spring. So the results that I'm going to be showing you are from that experiment, and that is the experiment that you're going to visit tomorrow during that field tour. So we have 4 different blocks, and each one of those with those 5 treatments that I just described. If you look at Google Earth, you can see where that experiment is located. Pretty marked differences already in the plant community composition, and you can just see it from imagery, which is really neat. So in terms of canopy cover of Kentucky bluegrass, we've managed to reduce bluegrass with all of our treatments except for our season-long grazing, which is kind of our control. However, the fire treatments have shown a much more significant reduction in bluegrass than our mob grazing treatment. So mob grazing, we're grazing really heavily. We're grazing 20 yearling steers in 1/4 of an acre for 24 hours, for those who might know what that means. So it's pretty intensive. And I'll talk about the trade-offs of grazing at that intensity too. So we've seen some reduction in bluegrass. Most of the reduction has happened, however, with the prescribed fire treatments, and especially the prescribed fire and grazing treatments. And if you think about the disturbances that these areas evolved with, it was a periodic occurrence of fire. There was a fire return interval of about 5 to 25 years, so this area evolved with fire, and large herds of bison moving through the prairie. So it evolved with grazing and burning, and that happens just to be the treatment that's working best for us in reducing bluegrass. And we're trying to reduce that bluegrass below 35%, because what we've heard, mostly anecdotally from NRCS and others, are that below that 35%, if you maintain that bluegrass below 35%, we can maintain a plant species diversity of some of our natives. So even after, what I'm showing you is about 4.5 years of treatment. Our next year is our last year of this experiment. So even after 5 years, we still, of burning and mob grazing, we still haven't gotten that Kentucky bluegrass below 35%, but we have been able to increase some of the native species diversity. So we're seeing some of the forbs, perennial forbs, deeper rooted forbs come in. We're seeing some of perennial grasses come in. And as you're walking there tomorrow, like I'm showing you all these data, all these graphs, you can actually see it as you're walking by. You can, very marked differences between the treatments, which is really neat to see just by walking out there and looking at the effects of these fire treatments and mob graze treatments. In terms of species richness, we've seen some increases for our mob graze treatment, but most of the increases come from those fire treatments too, and most of the increases have been in our warm season grasses, which is neat and is something that we're kind of going to explore more as this phase, where this is a 5-year experiment. It ends next year, so we're going to start trying to seed in some of those warm season species, kind of thinking about climate change and that warmer weather that we're expecting, warmer, drier weather. So how can we be proactive and start adapting our rangelands to those changes by incorporating more warm season species, native warm season species. So Dr. Liebig, Mark Liebig, who spoke earlier, he's done research, he's doing the soil component of these plots. So when I said those mob grazing treatments had some trade-offs, one of the things that we've seen is the near surface soil physical properties. They have changed before and after grazing, the mob grazing. We've seen a lower infiltration. We've seen some compaction in terms of that mob grazing treatment, really heavy treatments, and less hydraulic conductivity. So those mob treatments do carry some trade-offs that we need to consider, even though they are reducing some of the bluegrass, and they have had an effect on bluegrass and increasing some of the native diversity. It does carry some trade-offs. At the same time, fire does carry some trade-offs too. Kevin alluded to it. There's a lot of resistance to fire in North Dakota, and there is a risk associated with it. Most of it is perceived risks. There's ways to reduce those risks, but not everyone will be able to do either practice. So it's just kind of trying to provide tools for landowners to use and adapt to whatever their management operations are. So these are just data from 2021, 2022, kind of following up on that same slide of the hydraulic conductivity. So to conclude, what we see today, so I presented 5 years of data on that mob graze treatment, fire treatments, is a product of many, many years of change. So bluegrass has been here we actually have samples in our herbarium from 1916, and it's been here before that. But it kind of stayed at very low levels, and then in the 80s it just started going up. So what we've seen is many, many decades of change that has led to what we have out here right now. And in 5 years we've seen some change, but it's going to take a lot of time to revert those changes to wherever we want to go, wherever we want to take these range lines. So change is not instantaneous, it will take time. And we've seen that a combination of prescribed fire and grazing actually does help reduce that bluegrass and increase our native species diversity. We're seeing that shift in some, with our fire treatments and bringing in some more of the warm season grasses, getting rid of some of the invasive cool season grasses. So we're starting to see that shift, which hopefully will have some positive effects on ecosystem services that these grazing lands can provide, especially in terms of forage productivity and extending the length of that growing season, but also in terms of rooting depth, rooting type, and all the different things that that plant diversity will bring. And again, the impact of the changes that we're expecting in climate are going to be very context specific, so taking into account the areas that we're working with, or working in, and the types of operations and even human systems that we're working with are going to matter a lot. And as I mentioned earlier, our next phase is going to be incorporating some of those warm season species into our experiments. So with that, I think we have quite a bit of time for questions, if you have any. And if not, I got you to lunch way earlier.
Do we have some questions or comments for David? Forgive me.
There's one. If it's about soils, ask Mark.
So what you're presenting here is really interesting, really have interest in seeing what you're going to publish out there. We have a lot of problems with Kentucky bluegrass in the Southwest in our mountain and alpine meadow systems. My question for you is the fire, something we can do, very promising. Are you burning during what would be the traditional or what naturally would occur fire season, or are you doing off-season prescribed burns?
So fires would have naturally occurred during the hot, dry part of the year here, which would have been summer. We are burning in the fall. And the reason we're burning in the fall is because of climate change. Our burning window during the spring has been really reduced. So the amount of burning or potential burning days during spring or spring, summer is very short. Things green up, it's very hard to burn in summer, and early in the spring, just weather patterns have not been conducive to really burning. So that's why we decided to, because we wanted to be consistent with how we burned, and we know that we have more potential burning days during the fall, we just started doing fall. And it coincides with, so here in the Roan Plains, Kentucky bluegrass has 2 growth peaks. So it kind of early in the season, it has a peak, then it kind of slows down, and then later in the fall, when it cools down again, it starts growing again. We try to hit that second peak, so when it's actively growing, and try to hurt it that way.
We try to limit a lot of our burning to the off-season times.
What was that, sorry?
We try to limit a lot of our burning to the off-season time, so the fact that you're having that much of a reduction doing off-season burns is pretty encouraging, and I look forward to your publication of your work.
Yeah, and I think a lot of what we've been able to do with, or why that is working, is something that Kevin also mentioned. We're burning off that thatch layer, burning into that root mat layer. So I think that's part of the effect that we're having, opening up space.
All right, thank you.
Thank you. Good question, thanks.
Other questions?
Well, I know you're working with Kentucky bluegrass, but is there any brome in these pastures, and is there any research data that you associated on the sideline with the brome grass reduction or anything?
Most of these, so the pastures, the plots that I have, they're mostly Kentucky bluegrass. There is some brome, and we have seen some reductions in the brome too. So, but really it's very little compared to the amount of bluegrass we have in these pastures. And we picked these pastures specifically because of the amount of invasion of bluegrass. We even have some crested in there too.
Thank you, David.
Thank you.
It's lunchtime, folks. Dave, oh, okay.
So if you have a poster and you haven't gotten it over to 432 yet, now is your last window.
Good afternoon, folks. Hello, everybody. I'd just like to ask you. We've got our luncheon speakers here, so if we could keep our table chat to a dull roar, as they used to say in Boy Scouts, I'd appreciate that. I'm pleased to introduce Ed Murphy, who is the North Dakota State geologist and has been for some time. Tremendous experience in our state, and it's a pleasure to have him as our luncheon speaker.
Thank you, Ed.
Thank you. Thank you. Well, I'd like to start off, this to me is one of the nicest places in North Dakota. It's Logging Camp Ranch. I'm hoping I get this right. There we go. This is one of these areas from the top of that butte, that peak, to the bottom there. You can see some cottonwood trees. Right below that's the Little Missouri River. That's 500 feet. So if you've seen the state capitol here in Bismarck, you stack 2 of those and you still need a 50-foot ladder to get up there. You can see our drone. We'll be talking a little bit about that, the Phantom 4, $1,500. It's amazing what you can do with that. Just a quick note. So you've all got state geological surveys in your state. We've got 23 FTEs, so we're a small to medium survey. 14 geologists. We're a little unusual in that we have a paleontology section. We've got 3 paleontologists and 1 paleontology technician. They do 90% of the outreach for us, and so that really works out great. We also have a core and sample library at the University of North Dakota. We're headquartered here in Bismarck, but in Grand Forks we have a core and sample library. We've got 92 miles of core. 90-some% of that is oil and gas. And we started photographing that core in 8-inch segments 19 years ago. We just are short of 50%. We'll get to that later this year. Generated 360,000 feet, or 360,000 photographs. We also have thin sections. I love when I have to go to the doctor and he talk about, we'll take some skin cells and we'll do this and that. I said, yeah, we do that with rocks all the time. Look at them under a microscope. And so we've got close to 20,000 thin sections. We photograph those in quadrants under 2 types of light, plane and polarized. So that gives us 8 photomicrographs per thin section for another 140,000. So we just went over 500,000 photographs on an oil and gas subscription site. So industry is very appreciative of that. If I'd been on the field trip on Sunday, going over to Medora, when crossed over Glen Ellen, you might have noticed there were 2 flat valleys with little creeks in those, undersized creeks. Those are glacial meltwater channels, and they extend from up north near the Killdeer Mountains down in towards Fort Yates. The big thing you saw, though, in the Badlands, this is off of Google Earth, but we're looking to the southwest. You can see Medora is labeled, and there's a couple plateaus where at the position where the Little Missouri, the ancestral Little Missouri was flowing till it cut its way down to the present position. And then, of course, the Badlands themselves. And so those rocks are anywhere from the south part of the Badlands up to through the north side. You were kind of in the middle at Medora. But those rocks are anywhere from 65.5 million years old, which is when the asteroid hit down in Yucatan and wiped out the dinosaurs, up to 56 million years old, a little bit further north. And so they're alternating, they're part of the Fort Union group. They're alternating, they're non-marine rocks, alternating sandstones, siltstones, mudstones, clay stones, and lignite. And wherever that lignite is burned and baked the overlying rocks, then we get clinker, or what everyone in Western North Dakota calls scoria. And you might have noticed if you got off the pavement onto those reddish orange roads, those are, they use scoria or clinker to cover those. So when we look at the age of those rocks and the environments of deposition for the 60 million year old rocks, they were deposited in environmental or subtropic environment. I always tell people if you're around in North Dakota when these rocks were being deposited, you would have had a hard time keeping your feet dry, full of a lot of large river systems, a lot of swamps where peat was being deposited. Again, North Dakota, all of our coal is lignite, which is the soft brown coal. Probably 3 feet or so of peat was compacted to 1 foot of lignite. And so primarily we're, as far as fossils that we find in there, crocodiles and turtles, and then small mammals. Then we come up to Square Butte, which I'll show the next slide, another picture of that. But you might have noticed that when you're in that area, the prominent butte to the southwest of Medora. And there we jump up 20 million years, we're up to 40 million. And those rocks were deposited in more of a temperate climate and more like along the plains of Africa. We had much larger mammals, titanotheres and rhinoceros. And so you can find those bones up on the top of Square Butte. Photograph from one of our geologists, just from off the edge of that big plateau, that terrace I pointed out earlier. And again, Square Butte in the distance. So we're looking at 600 to 700 feet of relief difference over that 20 million year span. And then in this area, they call it petrified forest. You can see there's a lot of fossilized tree stumps. Most of these are Don redwood and bald cypress. Okay, so the field trip, the next field trip you'll be taking, I took the route and then I dropped on the surface geology map. And just, we'll go through a couple things. Here in the Bismarck area, we're still in the Fort Union group, but now we're in the Cannonball Formation, which is deposited in a marine setting. So there's no coal in the Cannonball. It consists primarily of about 2/3 mudstone, which gets to be a problem in the Bismarck-Mandan area because of the swelling clay component within that mudstone. And then 1/3 is sandstone. And the primary fossils we find there are shark's teeth, like from the sand shark, that type of tooth. Then going north, you'll be running back into the non-marine rocks, going up through the slope, Bullion Creek, and then the Sentinel Butte. The Bullion Creek and Sentinel Butte were the rocks that you saw in Medora. And then on both the north side and the south end of the trip, you're primarily in glacial. I don't know about mapping soils, but I know that mapping geology when you're in an area of mixed, where you've got thin glacial cover over older rocks, I found that to be the toughest. You've got to have much more control than if you're in one environment or the other. Got a couple pictures of woolly mammoth because just 15 miles, see if I can get this to work. 15 miles west of there is where 3 weeks ago we were notified by a company that they found a beautiful woolly mammoth tusk. So we went up there, and our paleontologist, I was up there for a day. We spent 3 weeks, parts of 3 weeks, looking for more. And the original tusk was found in a outwash deposit from the melting glacier, the rivers coming off that, which we do find a number of occasional mastodon or mammoth teeth or an occasional bone, but it's unusual to find an articulated skeleton. The environment, the energy was just too high. So we spent that time. What we found is most of a pelvis and part of a shoulder bone, but I think that's probably going to be it for this individual. So now our paleontologists, they have a great job, I think. So now they're spending 3 weeks just south of Bismarck here on a dinosaur dig. We've been digging there with the public for 7 years. We've found, this is a Tyrannosaurus rex reproduction over on the right there. We found over 18 T-Rex teeth And even the most hardened paleontologist that's used to finding hadrosaurs, which are duck-billed dinosaurs or triceratops, when they find anything related to T-Rex, they get pretty excited. Unfortunately, T-Rex shed their teeth. So, of course, every time you find a tooth, you work back looking for a skeleton, but we're yet to find one. I'm going to talk about Lewis and Clark because you're going to be going along the river and coming back along 1804, so you're going to be within the visibility. You can see the river. I did this book back in 2003 when everybody jumped on the Lewis and Clark bandwagon. Somebody had already done a recipe book, so we decided to do a geology book. Luckily for us, believe me, I mean, everybody was doing everything related to Lewis and Clark, but luckily for us, a fellow by the name of Martin Plamaden had reworked Clark's notes, surveying notes, and so we had his material. He had repositioned the campsites and the position of the river at that time. So that made it easy for us. We just came in, grabbed the journals, looked at the entries over a certain amount of area, and then looked at the scientific observations they made. And in this area, they're talking about, they go past Square Buttes. And this is Square Buttes north of Bismarck. And luckily, again for us, we had a local amateur painter by the name of Vern Erickson, who was painting a number of the scenes what Lewis and Clark would have seen in North Dakota, and we were able to use those. In fact, so here they are on October 23rd, 1804, coming up, and then we're looking to the west, and with Square Buttes in the background, so you've got Cannonball Formation, that marine unit at the base, and then you go up through the slope, Bullion Creek, to the Sentinel Butte, capping the top of that, so you'll be seeing that. So for a lot of this stretch between the Garrison Dam and Bismarck, the river would look very much like what Lewis and Clark saw. The one big difference is the clarity of the water, because Peck Dam and Garrison Dam are big sediment traps, essentially. So they're along the shore, you can literally see down to the bottom, which if you compare to what they saw, this is over on the right side, that's water that was picked up at the Bismarck water treatment plant just right down here in June of 1937. And you can see why the Missouri was called the Muddy Missouri. And then I picked up that jar, I picked that up in June of 2003. So pretty significant difference. Now we come up, I want to talk a little bit about Fort Mandan. Lewis and Clark spent the winter in Fort Mandan. That's the longest they were in any one place along their journey. And so we're looking to the southeast, so you can see that little star. You'll be going right by that as you go from Highway 48 to 200. And that's where we believe Fort Mandan existed. And this is a replica about 8 miles to the east of it. It was built in 1972. It's interesting, we looked at Lewis and Clark journals as well as the sergeants, and they talked about, these guys were from the east, they talked about how cold it was. It got down to, depending on what journal you looked at, minus 35, minus 40 Fahrenheit. By that time, they weren't quite as excited as they were at the beginning with those cold temperatures. But there was a big push to find Fort Mandan. Now, Fort Mandan burned. Clark, coming back through in 1806, August of 1806, noted that the fort had already burned. And there was just part of a building left, and of course the pickets below ground level. So there was a big push to find the fort. A fellow by the name of Klemensky thought he had found it. We took you can see there's a rectangle there. There were 2 attempts to determine